Ladies and gentlemen, good morning. Welcome to the second day of the Cybersecurity R&D Workshop, a virtual event held in conjunction with Singapore International Cyber Week 2020. This workshop is organized by the Singapore Cybersecurity Consortium under the National Cybersecurity R&D Program. It brings together cybersecurity R&D stakeholders from government, industry, and academia for cross-pollination of ideas to better direct research efforts to solve challenges on the ground. Yesterday, the workshop kicked off with the AI security track, and we learned many valuable insights from the expert speakers on trustworthy and responsible use of artificial intelligence in our systems. Today, we address the equally exciting topic of IoT security, with a lineup of distinguished speakers from the government, academia, and industry to discuss the different facets of security for the Internet of Things. To kick off today's program, we now invite Mr. Lim Soon Chia to deliver his opening keynote towards a secure and trusted IoT ecosystem. Mr. Lim Soon Chia is the Director for the Cybersecurity Engineering Center and Head of the Cybersecurity Certification Center at the Cybersecurity Agency of Singapore. In his current role, he is responsible for R&D and technology management, security engineering, as well as evaluation and certification. Previously, Mr. Lim held several senior leadership appointments in the Ministry of Defence and the Republic of Singapore Air Force. He was awarded the Defence Technology Prize in 2005 and the Public Administration Medal in 2007. Mr. Lim, please.
A big virtual welcome to all attending in Asia, as well as friends all over the world and across many time zones. Good morning, good afternoon, and perhaps good evening. Never have we imagined that this year we are meeting under such profoundly very different circumstances. On one hand, we're in the midst of a global pandemic, a black swan event, and biggest disaster that befall our generation. On the other hand, rather than things grinding to a slower pace, we are witnessing an intensifying and accelerating pace of digital transformation. COVID-19 has amplified the need for digitalization, sustainability, and resilience, and along with it, the growing importance of cybersecurity. With COVID, cybersecurity is not just important, but incredibly urgent. This year marks the 5th edition of our SICW, or Singapore International Cyber Week, and the International IoT Security Roundtable. And for the first time, we are dovetailing this annual R&D workshop with the bigger events. At the International IoT Security Roundtable yesterday, we brought together global thought leaders, policymakers, and experts in IoT from international communities. This afternoon, we have gathered deep technical experts and researchers from the industry and R&D communities to take us on a technical deep dive into the IoT challenges to kickstart technical work streams. All these are part of our effort and spirit to galvanize and engage global communities to achieve 3 S's: share, shape, and steer. To share ideas and experiences, to shape technologies and architectures, and to steer standards and best practices to build a secure and trusted global IoT ecosystem. We are an early vanguard in pushing for the IoT agenda. When we first started, there were a fair amount of tentativeness, but it has dramatically transformed over the last 4 years. There has been amazing proliferation of IoT devices and extensive connectivities. And with it, greater awareness of the cybersecurity concerns exacerbated by its short time to market and quick obsolescence nature of emerging technology. Today, we are seeing strong interest and increasing emphasis in the arena of IoT. Beyond the proliferation of IoT, we are also beginning to see convergence of IoT with artificial intelligence, or AI, steering towards a new wave of hyper-automation, whereby The orchestrated use of multiple technologies are catalyzing new waves of revolutions in efficiency, efficacy, and agility of business processes, as well as our lifestyle. And coupled with the accelerated digitalization, the tempo and proliferation of IoT is expected to intensify in scale, scope, distribution, and diversity. At last year's International IoT Security Roundtable, we did a Twin City joint release of the IoT Security Landscape Report, together with our counterparts from the Netherlands. The report identifies and discusses 11 interdependent IoT security challenges, grouped into 3 problem spaces. First, principles, governance, and legislation, where there's essentially a lack of standards to address security and privacy concerns, as well as legal liability. It was highlighted that with the quick obsolescence of emerging technologies such as IoT, the traditional evaluation and certification scheme does not seem to be compatible. Second, the ecosystem development, where we need to have a more responsible and security-conscious industry, and not one just to be able to design securely, but also to provide continuous maintenance and lifecycle support. It was noteworthy that with IoT being increasingly connected in the society and with distributed manufacturing, there's increasing concerns about the trustworthiness of supply chain. Third, technical references and standards, where we need to start to develop security standards to set baseline for security assurance and interoperability, and for export facilitation to grow digital industry and economy together. Beyond the landscape report, we also signed a joint statement with UK on IoT collaboration to recognize the 3 IoT baseline requirements that undergird the cybersecurity hygiene for consumer IoT devices. This year, as a follow-on, we are seeing the launch of our Cybersecurity Labeling Scheme, or CLS in short, the first such scheme in Asia-Pacific for consumer IoT or connected devices. The CLS is a response to the increasing security challenges brought about by the proliferation of IoT devices and their general lack of cybersecurity provisions. Its objective is to reduce attack surface, raise cybersecurity hygiene, and create a safer and more secure cyberspace. And the scheme achieves this through the use of a labeling targeted at C, D, and E. C for consumers. The CLS aims to help consumers make informed choices when purchasing such IoT devices. D for developers, to help developers to differentiate their products in the market and incentivize developers to produce more secure products. E for economy, to help grow digital economy through mutual recognition to reduce duplicated testing and improve market access. The CLS seeks to provide greater transparency for security of consumer smart devices by using a label to indicate the security rating of the product based on a series of security assessment. So for the first 2 levels, it is based on self-declaration to address basic security requirements as well as the adherence to the principles of security by design. Level 3 looks at software binary analysis to verify the absence of common known software vulnerabilities. And level 4, we are looking at pen testing to validate the resistance to common cyber attacks. We did not want to reinvent the wheel, and the criteria for CLS ratings references European Telecommunication Standard Institute ETSI's EN 303645, which is for cybersecurity for consumer Internet of Things baseline requirements. And this is widely adopted in Europe, notably UK, Finland, and also in Australia. And the use of a widely adopted standard will help to facilitate subsequent mutual recognition. For a start, the scheme is voluntary and is targeted at common consumer devices such as residential gateway, or commonly known as home Wi-Fi, and smart home hub. And this cybersecurity labeling scheme is not a static one. It allows us to progressively open up to new IoT device categories and also to continuously nudge the markets toward higher security requirements based on market interest, acceptance, and readiness. And this is done to strike a delicate balance of raising cyber hygiene while continue to encourage innovation and advance of new products. The threat and security risk of IoT is clear and present, and the IoT challenges are multifaceted. For today, we will touch on 3 technical challenges. First, architecture. Security and protection of IoT systems are very different from traditional distributed information systems due to scale, geographic distribution, diversity, and openness of the system environment. In time, we will see IoT systems coming together, each with their security priorities. For urban mobility encompassing autonomous vehicle, these concerns are its availability and integrity. For health, there's greater emphasis on integrity and confidentiality. And yet in others, non-repudiation may be critical, such as in financial services. How would a harmonizing reference architecture provide an integrated platform to achieve seamless interoperability and overall security? Professor Lang Kok Yen, a prolific professor at the Nanyang University of Singapore and a technopreneur himself, led a study on a reference IoT architecture. And he will later share with us a practical approach to this IoT security reference architecture through an activity network think, or in short, end-centric design. Second technical challenge, device identity and authentication. Given the pervasiveness of IoT and its freely plug-to-play modality of operations, asset disability and management is a serious challenge, unlike OT or enterprise IT networks. As such, IoT networks grow, identity and authentication is becoming an important part of endpoint security as part of a macrocosm that demands trusted identities and trusted communications to and fro all device types and the services. For IoT devices, a key challenge arises from being resource constrained, be it in terms of processing power and computing resources that limits the cryptography that it can run, or in terms of power energy that warrants a very tight power budget. For built-in identity and authentication, this could be challenging, given that such devices could not even accommodate a classical certificate-based identity implementation. Mr. Vishram Mishra, a co-founder of a startup, Microset, will share with us in the second technical brief on his development of his PKI-like security over constrained devices using micro-certificates. His team has successfully deployed this technology in a real-world sensor system and is revolutionizing security for systems with constrained bandwidth and computing power. The third technical challenge, secure communications and protocol. The key challenges for IoT networking and secure comms technologies arises from heterogeneity or diversity and conditions of IoT deployment that imposes requirements on mobility, scalability, manageability, reliability, availability, interoperability, as well as security, privacy, and trust. One such protocol that was widely used during COVID period was Bluetooth Low Energy, BLE, to the applications for the purpose of contact tracing application. Assistant Professor Sudipta Chattopadhyay from Singapore University of Technology and Design is an outstanding researcher under our National Cybersecurity R&D program. Earlier this year, he has done successive public disclosure of what he termed swan-tooth vulnerabilities, which are a spectrum of vulnerabilities found on Bluetooth Low Energy BLE system on a chip implementation. these vulnerabilities affect a multitude of IoT products, including medical devices such as pacemakers and blood pressure sensors. This afternoon, Sudipta will take us through a research tutorial on IoT protocol vulnerabilities and a research journey of his discovery. So, stay connected. It has been just 5 years since the formation of CSA, Cybersecurity Agency of Singapore. And this year's annual R&D workshops marks a significant, special significance for CSA as we stepped up to take over from NRF as a lead agency in driving the research direction, orchestrate the end-to-end value chain, while fostering closer triple helix partnership among government, industry, and academia to mature our cybersecurity research and innovation ecosystem. As we do so, we'd like to thank NRF for shepherding the cybersecurity R&D community in its early years. And right at this juncture, it is also timely for us to conduct a strategic review to envision what are our aspirations and challenges that lie ahead, and given our imperatives, what are our R&D big bets ahead. Here, I'd like to express my appreciation for the many people across the agencies and our ecosystem that are involved in this journey to chart the way forward for our research and innovation. Importantly, as our first outing with greater responsibilities on our shoulder, I'm glad that we are achieving greater reach and richness. First, on the richness, by bringing an international forum, the IIoT Security Roundtable, and our annual R&D workshop together for the first time, we're able to discuss and steer strategic direction and at the same time, deep dive into technical work streams. Second, on the reach, by harnessing on the opportunities available by COVID situation to be able to engage individuals and communities far and wide in a common pursuit to create a secure and trusted IoT ecosystem. In conclusion, the IoT challenges are increasingly cross-domain, multi-dimensional, and transboundary. We need to forge international collaboration. And through the R&D workshop this afternoon, we hope to explore deeper conversation to enable richer technical exchanges and cross-pollination of ideas. And on that note, I wish all happy networking and a fruitful event. Thank you very much.
Thank you, Mr. Lim, for the insightful keynote. We will now play a video on the Cybersecurity Labeling Scheme announced on Wednesday by Minister Iswaran and as mentioned by Mr. Lim in his opening keynote. Ladies and gentlemen, the Cybersecurity Labeling Scheme.
Singapore is embracing digitalization and is advancing towards it with Smart Nation as the vision for our future. Over the years, Internet of Things devices have seen an exponential growth and global proliferation. But generally, IoTs have poor security, presenting themselves as easy targets for cyber criminals to take control of the device, compromise data security and privacy, and launch cyber attacks just like the Mirai botnet attack that left key global Internet services inaccessible for hours. To improve IoT security and raise overall cyber hygiene levels, the Cybersecurity Agency of Singapore has launched the Cybersecurity Labeling Scheme. The CLS is the first scheme in Asia Pacific that seeks to provide greater transparency in the security of IoT devices using a 4-level rating label. The label allows consumers to discern the level of security offered by the product and imbues security consciousness when making purchases. The label can help manufacturers differentiate their products in the market and incentivize them to develop more secure products while reducing the cost of compliance across nations through mutual recognition. The Cybersecurity Labeling Scheme has 4 progressive rating levels. Level 1, meeting basic security requirements. Level 2, adherence to the principles of security by design. Level 3, absence of known common software vulnerabilities. And Level 4, resistance against common cyber attacks. With CLS, we aim to raise cybersecurity hygiene, incentivize developers to produce more secure products, and build a more trusted and secure cyberspace for everyone.
The next session will start at 10 a.m. For the first technical presentation, we are honored to have Professor Lam Kwok Yen, who will elaborate on the IoT Security Reference Architecture. Professor Lam is a professor of computer science and director of the Nanyang Technopreneurship Center at Nanyang Technological University, Singapore. He is concurrently serving as Director of the Strategic Center for Research in Privacy-Preserving Technologies and Systems and Director of NTU's Spirit Smart Nation Research Center. From August 2020, he's also a part-time seconded to Interpol as an advisor for cyber and new technology innovation. His research interests include cyber physical system security, distributed protocols for blockchain, biometric cryptography, homeland security, and cybersecurity. Professor Lam will take questions at the end of the talk. Professor, please.
In the next 45 minutes, I'm going to talk about our work on the security reference architecture of IoT systems. And so this work is conducted as a collaboration with the CSA under our Smart Nation Research Center. And so first of all, let's look at the motivation of this work. So in this work, we propose a generic IoT security reference architecture to assist in understanding security requirements and designing security architectures for IoT applications. Basically, when we look at Smart Nation applications, lots of them involve the deployment of a lot of IoT sensors or control devices. And because of that, we need to study the security requirements of applications that involving massive distribution or deployment of IoT devices, and then look at how to come up with an architecture that can help guide the design and implementation of such application systems with security in mind. And with this, we aim to promote the understanding of the interaction model, the system model, and the component model across all IoT applications. Basically, we need to look at the distinction between the IoT applications and traditional enterprise applications. We look at the difference and then we also identify the deficiencies of traditional enterprise security architectures when it's applied to IoT application systems. Now, given this deficiency in mind, we realize that we cannot do an ad hoc or reactive approach of adopting an existing enterprise security architectures for IoT systems and then try to fix the security problems in an ad hoc manner. So what we're trying to do is be more holistic and adopt the security by design principles. So we would like to come up with the security architecture for IoT systems with security in mind right from the beginning. And because of that, we need the architectures to be generic enough so that we can use it to cater for different types of IoT applications. And it also need to be flexible enough so that it is possible for the system owners to adjust the security control or the security strength depending on the nature of the applications. So because of that, we need to have a better understanding about the way that IoT applications interact, how the system look like, and what are the components involved, so that we can make a comparison and study the security architectures and compare with the traditional enterprise security architecture. And we aim to make use of this to guide the selections of security mechanisms that can be uniformly applied across an IoT systems. So first, as mentioned, we need to look at the characteristics of IoT systems so that we can identify the difference. We can identify the difference between enterprise security systems and IoT application systems. So we now look at the IoT characteristics that amplify the security challenge. Of course, in enterprise security, in enterprise application systems, because of the connectivity to the cyberspace, there are lots of security challenge, but the issue gets worsened when it comes to IoT. First, from the system perspective, IoT systems involve a wide variety of devices collecting data of varying sensitivities and are connected through a highly heterogeneous network, which make it very different from the enterprise systems, where at least within the enterprise perimeter, you still have a better control of the network. And you can make it more homogeneous and apply more homogeneous and enterprise-wide security policies or control. Whereas in the case of IoT, because of the deployment of IoT devices potentially in the different locations, and also in order to support the connectivity of different devices in different locations, it's very likely that you have a very heterogeneous network. And of course, and the other thing is with IoT devices potentially be deployed to capture or to sense different types of informations, and depending on the nature of the informations to be captured, it could be of different sensitivities. So because of that, we also need to, as I mentioned earlier, give flexibility for the system owner to determine the level of security strength of the control mechanisms, so that we can come up with a eventual security architecture for the target systems that meet the needs of the application, meets the need of the business scenarios, as well as to meet the need of the security control. And the other perspective is the environment. IoT devices are generally deployed in an uncontrolled environment where communication mostly takes place over open networks. Now, this is also related to my point earlier about heterogeneous network. In this case, we specifically mentioned that because IoT devices could quite likely that they are deployed in the open environment or uncontrolled environment. Like, for example, surveillance camera on the roadside, environment sensors on the roadside. So these are uncontrolled environment, and they most likely will connect to the backend through some of the public network, which are open networks. So because of that, the risk exposure or the attack surface of such an environment is very different from traditional enterprise systems, which basically can allow the system owner to put things into the enterprise perimeter, and then at least within the enterprise perimeter, all the components are connected and is in a controlled environment. Whereas in the case of IoT systems, we see a lot of IoT or system components, especially IoT devices or edge nodes. They are deployed in such an uncontrolled environment and connected through open networks. So if you use a traditional enterprise security architectures to secure this type of application environment, you're likely to have either a very inefficient control mechanisms, because you can't assume anything on the environment, or at the same time, the security it will be very difficult to ensure. So this is the other perspective from the perspective of the environment of the IoT components. The other is the constraints of the devices. Even though IoT systems are deployed for sensitive operations in the field, the lightweight nature of certain devices pose practical constraints on performance, reliability, and security. Now, this basically means that first, we have a IoT applications or smart nation application involving the deployment of a lot of IoT devices, and they are deployed in a uncontrolled environment connected through a very heterogeneous and open network. And the device itself have a very limited resource to implement security control due to the practical constraint of the low-cost devices. And of course, now we're seeing the trend that the computing capability of IoT devices has been improving over the past few years. But as a generic or as a reference architecture, we cannot rule out the possibility that there are still IoT devices that still have more limited computing capacity. So that's why when we look at a generic reference architecture, we need to consider not only the higher end devices with sufficient computing capacity, we also need to look at the lower end devices. And the other is the identity, because from the angle of the security design and implementations, to a large extent, lots of security mechanisms where they talk about authentication, authorization, access control. At the back of it is always the issue of identification or identity. Now, when we have machines, a server or PC or workstations or appliance, it's easier to assign an identity, and it's easier to administer the identity of those devices. Whereas if you have a low-cost, lightweight IoT device being deployed in an open environment, and the issue of assigning or maintaining the identity of such devices is very challenging. So assigning identities, authenticating identities, and verifying the role and privilege of identities, identified entities in such a heterogeneous perimeterless network is very challenging and complicated. So again, the issue of identity is not new. It's just when you need to provide this type of identity assurance or identification infrastructure in a open, low-cost environment is a completely different scenario. So that's why overall, all these IoT fabrics are extremely porous and with obscure and often unclear attack surfaces. So that's why in this study, now after identifying the characteristics of IoT systems and which are important when we look at whether an existing enterprise security architecture will be applicable. So after we identify this type of characteristics, then of course we look at what are the challenges in order if we want to address them in a IoT application environment. So what we need to do is also to look at the network architectures, how are such device or components being connected. Basically, the connectivity is important because as an IoT Internet of Things, you need the way that the IoT device works is to a large extent depending on whether it has connectivity to the backend server. So looking at the network connectivity or the network architecture is an important part. And the other one is to look at the attack surfaces. Now, given the network architectures, we want to know what are the attack surfaces so that we can do further analysis about the risk involved in each of the system components or domains. Now, as I mentioned, after we identify those security characteristics, the next thing is to compare. Now, bearing this distinction in terms of system characteristics in mind, we want to compare traditional enterprise and IoT security. Now, firstly, IoT devices lie outside of the traditional endpoints and computing nodes and interact with the physical world in a different manner compared to traditional IoT devices or traditional IT devices. As mentioned, in traditional systems, you have a computer, you have a data center where you can implement perimeter network. You have physical security. So the environment itself within the data center or within the enterprise perimeter, it tends to be more secure. Whereas then the main issue is to manage the interface of the perimeter network to the outside world, as well as to enforce the communication security between these distributed locations. But due to the operational requirements in the field, many IoT devices must comply with stringent demand for performance, reliability, and resilience, which are quite unlike those in enterprise IT systems. And IoT devices are deployed in uncharacteristic locations, need to be handled very differently from traditional traditional IT devices in terms of management, monitoring, and servicing. For example, if you want to do remote, if you want to do a software upgrade or patching in an enterprise network, it's a lot easier compared to the situation when you have your nodes, whether it's IoT or edge node, when you have a nodes that is out in the open environment. So doing all this remote patching or remote device administration is a lot more difficult. And many IoT devices do not provide sufficient visibility into their operation state, software configuration, which is very different from typical IT devices. And also in contrast with typical devices, the capabilities of the IoT device are fairly limited in terms of the features and support for customizations. I specifically mentioned customization because let's say with this type of low-cost device, if you have a specific enterprise policy that you need a different types of security control mechanisms, and with a traditional computing node, even if you cannot modify the firmware, at least you can plug in some security modules or have some loadable security software to implement the security control. Whereas in the case of this type of IoT device, is difficult, if possible at all, to perform this type of customization or customized security mechanisms for the device. So overall, it makes it a lot more difficult, and it's very different from the IoT, from the traditional enterprise security systems. So to summarize, the security challenges involved include, firstly, we're talking about a large-scale deployment of IoT devices. And it's not just a small number of workstations or servers or client PCs. We're talking about tens of thousands of devices, IoT devices, and each of them are connected to the network, and each of them are subject to attack because they are connected to the internet. And it is not just about the number, and also geographically distributed. So now, of course, a very simple but not very appropriate analogy is, let's say, ATM machines. You can consider the ATM machine as a more complex IoT device that, but in this case, this device is not sensing, but is to control mechanical movement. So in this case, is to count and dispense cash. And they are geographically distributed. But even if we use ATM machine as an example, as I said, it's not an appropriate example, but let's use it for the time being. And even if we use the ATM as an example, ATM is, the scale is a lot less. We may be talking about thousands of ATM machines island-wide, but it's not to the extent of tens of thousands or even hundreds of thousands. If you look at the type of surveillance camera and temperature sensor we have. And also geographic distribution. And for ATM machines, it's still more restricted to areas with more people traffic and shopping mall outside or locations outside of the bank's branch and things like that. But in the case of IoT devices, again, for example, surveillance camera, the geographic distribution is a lot wider. It's basically almost every corner. So the number, the scale of deployment and the geographic distribution is very different. And some more, if you look at the cost and the capability of the ATM machines, is definitely many times higher than the low-cost IoT devices. So it's so as I said, it's not a good comparison, but at least it gives you a sense of the difference in terms of the scale and in terms of the capability of the device being able to protect itself. And there's a diversified data of varying sensitivity over the network. Because IoT device, because it's just Internet of Things, if we talk about capturing of data, it could be any types of data. As I said, it could be a surveillance camera, so we're talking about video data. It could be a temperature sensor or environment sensor, so it's numeric data. Usually it represents readings of the environment. So it could be different types of sensing devices, and different types could generate different types of data, and it could also be of different sensitivity. Like if telemedicine, the IoT device could be a medical device that's connected to the internet, and if it's a health monitoring systems, then the data is a lot more sensitive because of the privacy concern. So, and the data processing need to be done in a complex threat environment. As mentioned, if let's say that if the device is higher end, the device itself could potentially be performing some processing, but because the device is operating in a untrusted environment, uncontrolled environment, connected through a open network, so the threat environment is a lot more complex. And if the device is not powerful enough, and you need to make use of an edge node to do the processing, and then the data processing at the end is also in a more complex threat environment compared to the traditional enterprise systems. So with this, as I mentioned, we identify the distinctions between enterprise applications or enterprise systems and IoT systems. Then we look at the security challenges in the IoT systems. Then we look at what are the possible attacks and targets. So here illustrates some examples from the angle of the physical presence or physical location. It could be subject to physical damage because it's an uncontrolled environment. And of course, it's really a matter of vandalism. And in terms of the connectivity, it could be subject to the denial of service attack because of the network could be flooded by DDoS attack. And as a device connected or operating in an open environment and connected to the open network. So the device, the edge, and the communication could all potentially be tampered by intruders or attackers. And the communication certainly can potentially be intercepted, and therefore all this point to the need for proper communication security. And also with this, then we also worry about the integrity, whether a compromised device can elevate its privilege so that it can access from the device, access the backend server. We have seen reported incidents in the past that a IoT surveillance camera which was hacked, and the attacker can log in to the surveillance camera and elevates the privilege and use the camera as a stepping stone to access the backend server. So these are possible. And then the software stack of the device or at the edge, it also can be subject to software exploit and spoofing. So these are possible attacks that can happen in an IoT scenario. So basically what we are saying is all the attack on traditional enterprise system is still applicable to IoT systems. And they are applicable not only to the backend server, but also to IoT devices, which operate in a more complex threat environment and has less capability or less capacity to protect itself. So with this, we basically, if we look at it in a piecemeal manner, what we are seeing is so far there are lots of piecemeal type of security mechanisms like hardware security, system security, network security, and data or application security. And each part of the system or each layer of the systems, it has its own security mechanisms. Like with the case of the hardware security, the hardware could be used to establish the root of trust and implement tamper resistance and guard against side channel attack, for example. And that's specifically for the hardware layer. At the system level, we see mechanisms like trusted execution base, boot authentication, and things like that. And at the network level, we can have encryption, message authentication, and channel encryptions or virtual private network, and so on. So these are each of the individual mechanisms. Now the question is, we learned in the past experience of enterprise security, if we look at security mechanisms standalone, you're unlikely to have a secure systems. That's why we need the concept of security by design. That means you look at the whole system architecture in a holistic manner. You look at the interactions and connectivity among the components. You look at the threat environment and the attack surfaces, and then you deploy the security mechanisms. Usually one complement the other so as to make the different security mechanisms to work together in such a manner that you achieve the overall risk management. So this is the design philosophy that we adopted. That is, we assume a high risk or open environment. And because of this open environment, we propose or we adopt a security by design principle. So first, in such a open environment where we can't trust anyone, there's nothing we can trust in the open environment. So at least we need to adopt the zero trust principle, because the distributed, open, and porous nature of the IoT fabric doesn't allow valid assumptions to be made on the operating environment of IoT systems. As such, the zero trust principle becomes a key tenet in securing IoT applications. So basically, we still need to look at the operating environment of the system component or the subsystems. And then we see what are the assumptions we can make. And usually the assumption can only be enforced or validated through physical or hardware security. And if there's no physical or hardware security that provide a trusted or secure environment for the computing nodes. So basically, there's nothing we can do but assume a zero trust environment. So what are the things we need to do when we talk about securing IoT systems in a zero trust environment? Basically, we need to identify the most critical and sensitive data assets and services, because there's so many components, and some are basically just a sensing environment. For example, you probably can have a number of sensors sensing the environment in a small area. So this, of course, gives you the flexibility to capture data that even to a small deviation within a small area. And also it can give you some resilience. That means if one device in that small area is tampered or compromised, you can detect because it's deviate too much from the rest. So this is just one example. But in this case, we don't consider this that critical. What we're talking about is whether there's any data or asset or service that if it's compromised, then the whole system will be compromised or will be jeopardized. So we need to identify this type of data or asset or services, and we call this the critical components. And the processing of this type of data is called the critical processing, and the node that execute this type of critical processing is the critical nodes. So the reason we need to identify this is we need to look at what are the smallest building block or subsystems that is processing sensitive data or critical data or performing critical operations that could potentially jeopardize the entire application systems. And then we will have to apply more stringent security control. And of course, because of the massive adoption of IoT devices and the wide geographic distribution, we can't possibly apply stringent security control everywhere. But at least we need to do an analysis of the security and the risk, and then we identify where are the critical activities. And then we need to make sure there is sufficient protection of the critical activities. So then we need to strictly enforce identification, authentication, authorization, encryption, and monitoring mechanisms for this type of activities. So, as mentioned, the design goals are based on this zero trust principle. With strong authentication mechanisms before an entity is granted access to sensitive resources or services, and origin and authenticity of data also need to be verified before they are accepted, for example, for being used as a supporting decision making. Because if the origin of the data is in doubt, then if you want to make a decision based on this dubious data, then your decision will not be very reliable. And schemes and mechanisms for assigning identities and verifying the roles and privilege of the identified entities to support strong authentications need to be established as well. And data generated or processed outside this, we so-called the secure micro-perimeters, could only be taken as a reference and should not be relied on for critical decisions. So what we mean is after we identify the various system components, the data, the processings, and their locations, we look at the environment. We look at the sensitivity of the data and the processing. Then we know we need to enforce stricter security protection of those critical data and processing. And in the architecture, we try to group them together so that we can form a micro perimeter in a smaller geographic area, whether it's through physical security or hardware security. But at least we know these are the critical activities that we cannot afford to take too much risk. So that's why we introduced this concept of micro perimeter so as to assist the adoption of the zero trust principle. But in this case, the design challenge is it provides means for system. We need to provide means for system owners to determine the sensitivity of the data. Of course, just now we've been trying to parameterize the discussion. We keep talking about sensitivity of the data, but the notion of sensitivity vary from application to application, from system owner to system owner. So we need to leave these decisions to the system owner. We cannot have a one-size-fits-all approach that I don't care whether it's sensitive to you, but I just make it strictly protected for you as well. That in this case, you will have an overkill system that is too inefficient for use. So that's why in the architecture we need to provide this type of flexibility to allow the system owner to determine the sensitivity of the data and the criticality of the activities that process this data. The sensitivity may be inherent to the nature of the data or due to the environment within which such data are acquired, or due to the nature of the data processing. So given this, and then we need to develop a holistic and modular framework for risk assessment and analysis of the security requirement. And so this is another challenge, how to come up with such a holistic and modular framework. And overall, we need an effective application of a risk-based security design. Again, we always emphasize the risk-based approach because we don't believe in a one-size-fits-all type of security design. Even though we come up with a security reference architecture, but this reference architecture provides a framework and with flexibility for the system owner to determine the sensitivity level of the data and the strength level of the control mechanisms. So with this, another one is the flexibility to configure the security level, as I mentioned, and the control measures based on the current standards commensurate with the practical risk of an IoT system and promoting secure functionality. So we also always believe that you want to promote adoption of security, you need to encourage security by design. That is to design the security architecture right from the beginning and give people the flexibility so that they can take a risk-based approach rather than a one-size-fits-all approach. So these are the challenges. So how do we approach this problem? First, we need to understand the IoT architecture, but because IoT is still an emerging area, even when we start this project 2 years ago, it was still an emerging area. And even though so many people are talking about it, and there are so many pilot implementations that people discussed, but actual large-scale deployment of IoT systems was still in experimental stage, and there's not much document experience on this. So we need to find a systematic way to understand and study the system architecture of IoT applications. So with that, we make use of the 3 different perspectives in terms of system architecture perspective, adopted from the IoT research community. The first is the device-oriented, which focus on the functionality, limitations, and characteristics of devices. And the second is the internet-oriented, that focus on the network integrations platform supporting connectivity of the devices. And then it's a semantic-oriented that focus on the data and knowledge created from the processing of the data. In our work, we have devised an organized approach, namely the ANT-centric approach. A stands for activity, N stands for network, T stands for the things, that corresponds to the 3 system perspective of IoT architectures. So based on each of these IoT system perspective to study the characteristics of IoT applications. As a quick overview, the key features of this architecture framework, as mentioned, the ANT, the activity-centric, it helps to understand the context of system components, identify critical nodes and activities where sensitive IoT application data are stored and processed. And then the other architectural aspect is the network-centric, which helps to understand the connectivity among all components and thus to identify the flow of sensitive data through the system. And it also helps us look at identify the attack surface and study the threat environment of each of the network segments. And then it's the thing-centric, which helps to understand the nature of the security issues of heterogeneous data acquisition from diverse devices. And so, as I kept emphasizing earlier on, the activity-centric perspective is very important, because basically we can't possibly protect everything, but we need to identify what are the most critical data and processing. Then we focus on protecting them. We may even need to adjust the architecture so that we put them in closer proximity, and we can define a micro perimeter. So the things and the network-centric views basically are to complement the security understanding of the activity-centric view. So this is the methodology and flow of our architecture study. We identify the intended features of the IoT systems, and then we determine the distinguishing features of the IoT system which are most relevant for security by design. Then we analyze the risk and systematically study the security requirements based on the architectural views. Then, as I kept emphasizing, identify the critical activities that involve acquiring, storing, transmitting, processing, and interfacing with the sensitive data. Then we instantiate the security control measures, determining the notion of data sensitivity and activity criticality from the organization perspective. That means from the system owner's point of view. So this is the part that we leave it to the system owner to decide. So just now we keep talking about critical activities. Here I give some an overview about what we mean by the critical activities. So first is to identify the critical nodes. That is activities performed on these nodes are referred to as the critical activities, which if compromised will lead to negative impacts on the entire systems. So this is done by the practitioners while designing the system's functional components. And control measures are then mapped to each critical activity performed by specific critical nodes. And this is the job of the practitioner who has the basic understanding of the role of control measures. And the proposed architecture also offers some level of choices of security recommendations depending on the data sensitivity. And of course, this sensitivity depends on the impact of attacks on the organizations. So basically, we take reference to the FIPS 199 and the NIST special paper 800-63 to look at the notion of sensitivity and how this notion of sensitivity affect the security control measures. So with this, basically, is an overview about the IoT reference architecture. The full report can be downloaded from our public website, so for the purpose of this talk, we only aim to give you an idea about the design, the motivation, the design philosophy, the architecture approach, and our methodology, and what are the key considerations when we design the IoT security reference architectures. This is an overview where we divide the network, the IoT application into the things layer, the network layer, and the backend, the platform layer, and application layer. So from this diagram, you more or less can tell the locations of the various components, the openness of the environment of those locations, and the connectivity involved. As you can see in the network layer, many different types of network technologies are being supported or adopted. So one example is the smart lamppost. I choose this because when we did our survey, lots of countries adopt the smart lamppost as one of the example applications. Where even cities in Asia, a number of cities in Asia also adopting the smart lamppost as a kind of smart city applications. So basically, when we look at study the security reference architecture for smart lampposts, we look at the system features because they basically tell us what are the things are needed by the smart lamppost, like temperature and humidity sensors, which is integrated with the microcontroller mounted on the lamppost, IP camera mounted on the lamppost, and then probably with some wired Ethernet connectivity from the IP camera to the lamppost itself, and some local gateway. And then there may be some collected data from the sensor or from the camera will be transmitted or delivered to some cloud platform. So these are the functionality. And as I said, we want to know this functionality because basically they tell us what type of devices or things are being required. So this gives you a quick overview about the various things and network-centric perspective, including from the smart lamppost, what type of IoT sensors, what are the interfaces to the controller, and from the controller or from the smart lamppost, what type of network connectivity is being needed to connect to the backend. And potentially we'll have some edge computing node as well. So with the things and the network-centric views, they help us a fine-grained analysis of the risk and security requirements. So this at least will tell us that it's different from an enterprise system. And it is not something that we can do in an ad hoc manner. And like what I mentioned, we can do it in a very piecemeal way, hardware security, system security, network security, in a very ad hoc manner. But this systematic way to look at the overall architectures from the things perspective and from the network perspective allow us to analyze the security requirements in a more fine-grained manner. So in terms of activity centrics, so we identify what types of data are being captured or processed and which type of data are sensitive. So it helps to identify the nodes where sensitive IoT application data are stored and processed, and to determine the critical activities of the IoT systems. I'm not going to go to the detail, but it gives you a quick overview about the process of coming up with from the IoT security reference architecture and how to instantiate into a specific security architecture for a particular smart nation application or smart city application. So the security requirement that is resulted from the thing-centric or from the ANT-centric architecture is important because it helps identify areas of the system which, if compromised, will lead to negative impact of the entire system. And we define such areas as critical nodes, as I mentioned, because if they fail, then the entire system will be jeopardized. So here we identify some of the critical activities at the IP camera, the IoT gateway, as well as the backend cloud. So this is how we map the critical activities in the smart lamppost from the nodes to the protection requirements. Again, this is just for completeness to show you the process. And from the critical activities to the security control. As I said, if you look at each of these individual building blocks, it's like piecemeal, but at least if it's applied through the framework of the IoT security reference architecture, at least we know we are doing in a systematic and holistic manner. Because the architecture framework itself is derived from the security from right from the beginning, from the security by design angle. So this is what we obtained by applying the characteristics of the smart lamppost functionality to instantiate the IoT security reference architecture. Again, I will not go through the detail here. The purpose is for completeness to show you the process, and you can download the full report from our website after this. So to conclude, We did a comparison of the classical IT paradigm in contrast with the IoT paradigm in order to identify distinguishing security characteristics of IoT systems. And comparative study revealed that the open system security model based on underlying zero trust principle is really neat to govern the security architecture design of IoT systems. And then we translated observed distinguishing characteristics into features and requirements of an appropriate system architecture design. And we determined the architectural features of IoT systems that are most relevant to the security by design of IoT applications based on the ANT-centric views. And then we design and develop a generic framework to identify suitable mechanisms to implement the appropriate control measures in order to meet the security requirements at individual nodes, and most importantly, the critical nodes. And then is to instantiate and verify the generic framework using practical use cases from large-scale IoT application implementations like smart cities, for example, the smart lampposts, smart metering, and smart home. So with this, I conclude my my talk about this IoT security reference architecture. I will give you an overview about the motivations, the approach, the design philosophy, and the architectural methodologies that we adopt when we came up with this IoT security reference architecture. Thank you.
We will now have the Q&A session with Professor Lam, hosted by Dr. Vivi Suhendra, Executive Director of the Singapore Cybersecurity Consortium.
Good morning to all our virtual audience joining us here today. Thank you, Professor Lam, for explaining the reference architecture in depth. I understand you also had a brief discussion of this at the IoT Roundtable yesterday. So let's just jump to the first question. So we have a question here. Would zero trust be too strong and limiting for applications that are less critical?
Well, as I emphasized, there's no one size fits all, but at least we provide a realistic capture of the operating environment of the IoT systems. And of course, for applications that is less sensitive, then you can choose mechanisms that is, as you can see in the slide, we have different levels of security control for different types of sensitivity. So for applications that is less sensitive, and even though we're talking about the zero trust, it doesn't mean that you have to address all by all means. So that's why at least we give the flexibility for addressing this for situations where I would say whether the application is less sensitive, but maybe some of the data is less critical or less sensitive.
Okay. Yeah, thanks for that succinct explanation. So the next question we have is, since security could be focused on the impact for the whole system, but if it's about privacy, then it should be evaluated for individuals. So do we need different frameworks if we are going to tackle cybersecurity and privacy?
Okay, of course, privacy is usually an additional requirement, and we usually look at security as a mechanisms for satisfying or complying with the privacy policies or requirements. So I think fundamentally, I think this framework should be enough to capture the enforcement mechanisms for privacy data. That means when we talk about data being sensitive, it could be personal privacy sensitivity. So, but one key thing is about the situation that you have a IoT device which may not be capable enough to operate or to implement some of the security control mechanisms, but yet it is processing privacy sensitive data. Now, in this type of situation, we will have to look at the environment, and we have to apply the model of these critical activities and see whether we can form a microperimeter around this sensitive data, so that the device, which I think we have to get to see a scenario where you have a device in an uncontrolled environment which can capture privacy sensitive data. But if this is the case, most likely the data is captured in a physical environment where at least it's not publicly accessible. Because if, let's say you talk about a video recording, if the video recording is a public area, and we should don't say this video is privacy sensitive, because if you stand there with the camera, you can take the same thing. So coming back to your questions, I tend to look at the privacy more as a additional security requirement or enforcement requirement, whereas the security mechanisms that is captured in this or addressed in this IoT security reference architecture look at the enforcement mechanisms, which could be about operation security, and also it could be personal private data privacy as well. So I think the framework should be able to address that. But of course, security is always evolving. So when we see emerging application scenarios, then we will have to come back and review the framework and see whether the framework is still applicable in some of the emerging scenarios.
We probably just have one last question. It's a very practical question. Are there any good software development framework to use for building secure IoT application which achieve security by design and also considering limitation of IoT hardware?
I doubt so. In fact, this area is emerging, and since we started working on this few years ago, we keep seeing even the concept about IoT device being resource constrained. Even this concept is also evolving. Initially, we saw devices really resource constrained, but now we are seeing a lot of IoT devices. Thanks to the improvement in consumer electronics, probably we are seeing a lot of low-cost IoT devices which have computing capability, which can be as good as a PC 10 years ago. So this thing is still evolving, and because of that, a lot of software development framework, I think, is not to the stage that it is released for addressing all the wish list that was asked earlier. But I certainly hope that this could be an area that people will focus on. But to do that, a kind of reference architectures or system framework will be useful. Otherwise, it is very difficult to see how to put things together. Again, I also emphasize on the system security aspects of the IoT security. So I would say right now, I don't see something that is addressing all the wish list that was asked, but I think it should be an area that we should work towards.
Yeah. Thank you, Professor Lau, for the discussion. I wish we could go on, but unfortunately, that's all the time we have. So I would like also to thank our audience for your questions, and I hope you found this fruitful for you, and I will see you in the next session.
Thank you, Professor Lam, for the discerning session. The next session will start at 11 a.m. For the second technical presentation, it is a pleasure to have with us Dr. Vishram Mishra to address trusted identity of IoT devices in the supply chain. Dr. Vishram Mishra is the CEO and co-founder of Microsec, an IoT cybersecurity company in Singapore. He is a certified information security professional with a PhD in advanced wireless communication. He has more than 10 years of experience in advanced cybersecurity and in IoT. He has helped governments and MNCs solve cybersecurity issues and helped set up various policies. Dr. Mishra will take questions at the end of the talk. Dr. Mishra, please.
Good morning, everyone. I'm Dr. Vishram Mishra, co-founder and CEO of Microsec Private Limited. We are an IoT cybersecurity-based company. Today, we're going to talk about trusted identity of IoT devices in a supply chain. Before we get into that, let's look into the number of attacks which is happening in the past few years. During the first 6 months of 2019, the number of attacks increased by 300% in comparison to 2018. These attacks sustained during the last 6 months of 2019 as well. And we're going to see the numbers for 2020 very soon by the end of this year. Sources have confirmed that more than 6 trillion of damages will be done or caused by these attacks by 2021. And according to some of the other sources, 73% of these devices, which are already out in the world, have already suffered from these attacks. Now, one of the reasons which is attributed towards these attacks is that more than 80% of these devices are already vulnerable. Now, when we look into the entire IoT security, right, we have to look at it from different components, which basically plays their own part in their value chain. So for example, in the case of typical networks, right, we can see that we have got devices which are used by users, then you've got gateways, access points, as well as you got your cloud and applications, right? Now, according to where you're looking at cybersecurity, right, they have different components involved in it. For example, on the user devices side, we're looking at the device security. On the gateway access point, we're looking at the communication network security, as well as when we look into the cloud or applications, we look at the cloud application security. Now, although these are different, but from a security by design concept, or from the perspective of looking into the lifecycle management, we're to ensure that all three of these portions play their own part. Now, that being said, there are three most vulnerable areas in IoT cybersecurity. The first is authentication, including access control and data security, meaning that how do we actually identify who's who and who's supposed to access a particular device, and whether the devices are able to send the data in a secure way, and whether the particular data packet which is transmitted is also not tampered with. The second area is more towards supply chain or the lifecycle management. Supply chain indicates that when the devices are manufactured all the way from manufacturing units to the distributor, all the way to their user, how do we identify that none of the devices or none of the data packets or none of the data streams have been tampered with? Similarly, on the lifecycle management, the issue is to be ensured that how do we make sure all the authentications or the commissioning or enrollment or even updates are properly done. And of course, the third is the most common one is the intrusion tampering detection, meaning that how do we identify what kind of networks are there, what kind of devices are part of your system, and whether there's any anomaly happening or occurring in your network, and whether there's someone trying to tamper the network, is able to perform intrusion, become part of the system, or is able to compromise the system. Now, of course, when we look into these three most vulnerable areas, we have to look at from three different angles, right? But majority of the time, although they look different, but there's always an overlap. Now, let's look at the IoT supply chain, right? In the case of IoT supply chain, there are two things we have to look into. The first thing is that, are we talking about IoT devices through the supply chain, meaning that they are manufactured by a manufacturer where the raw components are supplied by a supplier and then distributed through a distributor, and then of course, at the end, deployed to a consumer via, let's say, a system integrator or maybe via a solution provider. So it means that we're looking at the devices through the supply chain. The other aspect is that where we talk about IoT use case in the supply chain. So for example, when we look into smart manufacturing, Industry 4.0, or smart supply chain logistics, right, where we want to do asset tracking, where we want to do control management, ERP application, and things like that. And of course, we use IoT in those scenarios. Now, when we talk about IoT in both the cases, the IT cybersecurity applications, or whether the identity are applicable in both the domains. Although in this talk, we will talk more about the formal use case here, it doesn't mean that the application are not applicable over the latter case here. Now, let's look at the supply chain for IoT devices here. In the case of IoT devices, right, you have a manufacturer which basically manufactures and devices while combining the hardware, software, as well as other components and other components and subcomponents. Now, these softwares can be provided by a third-party company. In most of the cases, it could be open source libraries, it could be some closed firmwares or closed packages, which is developed by a third-party company, or it could be the in-house software production unit, which basically have to customize and build the software solution. And of course, the hardware can be provided by any other third-party company, which is expert in, let's say, silica solution, or maybe a sub-module solution. Once the device is manufactured, right, it goes through a distributor to provide the system indicators, different varieties and different forms of devices. The system indicators then build the system with the help of the devices for a system owner. And in between, sometimes they also work with network operator, for example, telco operators or other operators, to ensure that they're able to become part of the entire network infrastructure. Once the system owner gets the system right, they either use the system by themselves, or they basically deploy some portion of the system for end user to use it. Now, depending upon how the system works, right, there are different permutation and combinations here. Now let's look at the entire supply chain one by one and see what kind of threats exist on the supply chain portions here. Now, let's look at the hardware, right? On the hardware side, the microcontrollers, microprocessors, or any other sub-modules, right? The potential threats include counterfeiting of the hardware components, meaning that you're able to compromise the random number generators, you're able to compromise the bus, the I2C interfaces, SPI interfaces, or maybe there's a backdoor which is provided on hardware itself. Meaning that, for example, someone is able to intercept the flash drive, someone is able to intercept the EEPROM or the RAM contents of the particular microcontroller. The second component is more to software, where we look into, let's say, backdoor-based implementation, where, let's say, a particular software has been implemented with the perspective of, let's say, admin login, or there's operator login, meaning that there's a backdoor inside it. Now, it could be intentional, it could be unintentional, or it could be malicious as well. Of course, the other issues which we see right now in software is the malicious or unintentional implementation of compromise function. It could be vulnerability through third-party libraries. It could be compromise implementation of certain functions. And of course, one of the malware that we currently see right now is more towards botnet. On the OEM side, we typically see different kinds of threats, but majority of the threats basically point towards insider attacks. Currently, more than 80% of the cyber attacks that we see on the supply chain are insider attacks, meaning that someone within your own company compromises the system. It could be intentional, it could be unintentional. It could be your ex-employee who's not happy with your company. It could be someone else who already knows about your system. He or she leaks the information over dark web forums and other forums like that. The other issues, of course, comes towards the compromise implementation of the system itself. For example, you have dangling USB ports, you have dangling UART interfaces or teletype interfaces to log into the system. And of course, let's say if you build a system from an OEM solution, right, you typically have management component inside it, which forms the backdoor for most of the vulnerabilities here. On the distributor side, what we're seeing right now is that when distributor distribute the solution through manufacturer, right, in between they could be swap of the devices. So you at the end you may see counterfeit devices which are being installed. Of course, the distributor can change the configuration, the factory settings, as well as they can additionally install backdoors on those devices. And looking at the system indicators, we see the same problem as we see in the OEMs, because majority of the time there is a operator or there is a human involved who's going to integrate the system. We see ex-employees or someone who already has deployed the system has a very good information about what kind of security components are used, what kind of keys are configured, and they are the one who basically compromise the system. And of course, they can also do wrong configuration. It could be malicious, it could be non-malicious, it could be, done by another party by bringing, let's say, a subcontractor or any third-party libraries which are being used to integrate the system. That there are various reasons because of which this could really go in a wrong direction. And of course, many times the system integrators also install backdoor to ensure that they're able to do updates, management, and majority of the time, these backdoors then become part of the entire issue that we face with the vulnerabilities. In terms of network providers, although this is not really a huge concern in a zero trust end-to-end security, but let's say in a system where you rely on network or telco operators. For example, when you use NB IoT-based systems or 3G-based network where you have private APN, right? You typically rely on network provider to provide you certain security configuration or at least the communication level security. So the issue is that in that kind of scenario, the network operator is able to sniff on the data packets. They're able to do man-in-the-middle attacks by tampering the data packets, which is going through. They're able to change how the system reacts and behaves from the network perspective. And of course, they can do impersonation attack as well. They can replace one devices as part of the network. They can add their own devices, and then they can replicate the behavior. And the third thing is more towards the insider attacks, because on the communication security side, when we look into key management systems or CS servers or root of trust, right, they're typically deployed by the admin team. Let's say if someone from the admin team has been compromised, meaning that your entire network deployment has been compromised. Similarly, when you look at the system owner itself, let's say the end agency or end user who's using it, right? When I say end user, I don't mean the user of the system, which is going to be deployed by the system owner. End user as in itself, meaning that who basically gets the system from the system integrator here. Some of the potential threats includes insider threats here. Again, the reason because you can have admin and employees who are compromised and they're able to change the configuration, they're able to change the data packet which is coming through, right? Similarly, they also have the functionality to do updates over the system as well. Meaning that, let's say if they believe that they have some of the systems where they can do compromise firmware update is going to result in certain functionality or certain behavior which could be favorable to them. In that scenario, they will of course perform these kind of updates. And the third thing which happens especially with some of the system owner from cost cutting point of view is that sometimes they replace devices and systems with counterfeit devices. And of course, it voids warranties and things like that. But of course, it adds additional surface attack vectors. From a user point of view, right? For example, the end user who are going to use the system from the system owner, it might be possible that they are able to update the firmware with their own firmwares. They're able to change the devices. They're able to do impersonation attack with their own devices. So although it will directly impact the end user, but they might do it unknowingly as well. For example, they thought that this device is going to behave in a certain way, and they went to online and they figured out, okay, they're going to replace this device because it's not behaving the right way, it's cheaper, or it has additional functionality, right? It might be possible that that particular device they're buying from web, right? It might come with some kind of backdoor, it might come with some kind of botnet and things like that. So when we talk about supply chain itself here, right, we're looking to different components which are involved in it. But how do these components really come into attacks, right? For example, have you seen these attacks happening in the world right now? Yes, we have seen these attacks. For example, one of the famous attack which happened on typical, let's say, IoT and IT systems was on ASUS-based networks and devices. For example, one of the utility which currently we use on the ASUS-based laptops, IT networks and devices is what you call ASUS Live Update. Now, there was a malware which you call as Operation Shadow Hammer, which compromised the ASUS Live Update functionality by injecting its own code inside that particular utility. Now, what happens is that you typically download this utility on your laptop, on your IT devices, or let's say your ASUS board, utility motherboards, and you try to actually figure out what kind of drivers you need on your let's say embedded board and maybe on your SBC and things like that, right? So on that particular side, what happens is that this utility, once it gets downloaded on your single board computer, SBCs, or on your embedded boards, or even your laptops, right? What happens is that it figures out what kind of drivers you need, what kind of updates you need to perform, whether you already have existing firmware or existing drivers for certain things. And in the meantime, it also tries to install a backdoor. So meaning that the utility that you used to use for updating your devices, your firmware, your drivers, is now also installing a backdoor on your system. Now, of course, this backdoor can be used for multiple reasons, right, or multiple use cases from the malicious intent, right? For example, attackers can use it for intrude, they can create botnet, they can do crypto mining and things like that. But when you look from the user perspective, right, users are not aware of it. The reason because they have the peace of mind that they download a utility from ASUS-based web server, and the utility is already well known in the industry. So what happens here is that it propagates in such a way that it's unknown to many people that they already have this kind of malware inside their laptops or their own single board computers. And now when we look into the entire supply chain attacks here, it happened on two components here. It happened on the software side and also on the OEM side. Software side, because the ASUS Live Update utility was compromised, meaning that the third-party components were compromised and they were the one who basically creates the backdoor. The second thing was that the software was signed by ASUS Tech, meaning that the OEM solution provider signed that particular software, which is verified by your computer. It could be Microsoft Windows, it could be Ubuntu-based Linux system, and they verified the integrity as well as the authenticity of that particular software. So it means that if you're able to compromise software, the third-party components, as well as OEM, you're able to do such kind of attacks. Now, this attack is not alone. We have seen that this is such kind of incidents happening in other areas as well. For example, when we look into other supply chain attacks, especially focusing on, let's say, Windows 7 based devices here, right? So there was an attack which we call Lemon Deck, which compromised autonomous ground vehicles. Now, autonomous ground vehicles are basically autonomous vehicles which are used to move certain objects, certain, your warehouse-based things from one place to other place. Now, what happened with Lemon Deck was that it compromised the vulnerabilities which exist on the Windows 7. And the reason it exists because Windows 7 has been outdated, right? There's not much support provided for Windows 7. So it means that attackers can figure out the vulnerabilities which has been disclosed for Windows 7, and then they are able to provide malware which can target those. Now, if you're using Windows 7-based implementations on any IoT-based solutions, for example, autonomous ground vehicles, Industry 4.0, or maybe other energy-based infrastructure, right? So in that kind of scenarios, you are able to compromise the system and you're able to create backdoor. Now with backdoor, you can do crypto mining, you can do DDoS attack like Mirai botnet, or you can do some other weird thing, right? In the case of Lemon Deck, they were doing crypto mining with this particular kind of attack here. Now, looking at the entire supply chain attack, right? When we look into the solution, of course, we know that the right solution is to do trusted INT-based protection, right? But how do we actually achieve this? This is something which is quite different from IT-based domain. Now, let's look at how does IT differs from IoT here, right? So in the case of IoT devices here, right, we have more than 35 communication standards. We have seen more than 10 kinds of microprocessors or processor architecture when it comes to IoT devices. So it means that when you have multiple combinations of, or heterogeneous combinations of protocols as well as processor types, the issue is that you're not able to follow a single solution, or just like what you do in IT, onto the IoT domain. Now, this is just not one problem. The other problem also exists onto the computing and resources which is available over these IoT devices. Now, most of these IoT devices, they typically have very small amount of computing power, very small amount of resources, including bandwidth, which means that your traditional IT-based solution for trusted identity will not work over these devices. For example, a typical IoT device will have RAM around 4 kilobyte to 10 kilobyte. The gateway-based solution will have between 128 megabyte to 256 megabyte. Whereas your IT solution has ran between 2 gigabyte to 8 gigabyte and 16 gigabytes, right? So that the kind of solution that you expect on the IoT is going to be very different. Now, the other issue is more towards that we have seen multiple standards, especially from cybersecurity point of view. For example, when you look into LoRaWAN, NB-IoT, Zigbee, Bluetooth, and all these communication protocols, right? They typically have their own way of handling cybersecurity. Meaning that when you try to provide trusted identity on those devices, it's going to vary from protocol to protocol. For example, when you want to do Bluetooth-based implementation, you have to follow the Bluetooth SIG-based standard. Similarly, when you want to do with LoRaWAN, you have to follow the LoRaWAN-based standards. So it means that depending upon the heterogeneous network that you have to cater to the different requirements of the protocol, which becomes quite tedious. Now, the other part is more towards the non-transparency. When it comes to IT-based systems, right, you can ask the vendor, what are the software provided, what are the applications installed, and it's actually quite transparent. And even though it's not transparent, you're able to figure out, based on the spec sheet, you're able to figure out what things you need to do to ensure that whether you're able to make it transparent. For example, what sort of driver was provided, what is the version number, and things like that. But when it comes to IoT devices, right, we're not able to see that. For example, if you go to a vendor and ask them what kind of library was installed for communication segment, what is the exact version of AES encryption used, whether it's the CTR-based mechanism implemented with this particular algorithm, whether it's a cyber attack or not, and things like that, it becomes very tedious. Of course, you can do pen testing to actually get some of the information, but of course, you won't get the entire information. Now, when you look into trusted identity, right, we have to look from different perspective. So for example, we have to start with zero trust. Zero trust meaning that we have to do mutual authentication or two-way authentication. And we have to make sure that there's end-to-end encryption session for everything, whether there's a packet transfer, whether there's a data transfer, whether there's any control information, or whether any other kind of information. Now to do mutual authentication, you can use PKI, you can use KMS, you can use CLP, the certificate-less protocol. And there are other protocols which exist in the market right now. But you have to keep in mind is that when it comes to IoT, you have to see the original problem that we discussed. Problems where they are resource constrained, they don't have enough computing resources or bandwidth resources, they are multiple standards, and they have heterogeneous protocols. So meaning that you have to choose a solution which is able to cater to all those requirements. Similarly, you have to use digital signatures. Now, to use digital, we have been using digital signatures in the IT domain for quite some time, right? You use certificates, you sign documents, you can sign the firmware and things like that, right? In the case of IoT, because of their constrained resources and bandwidth requirements, right, you have to ensure that you're able to use signatures which can work over embedded devices. To give an example, right, you can use elliptic curve-based signatures, for example, Edward curves, or you can use Nice-based curves to ensure that you're able to sign the firmware or services or software or data to ensure that you're able to provide trusted identity here. Similarly, you have to use multi-factor trust, meaning that you can use OTP, authenticator, or you can do maybe offline-based onboarding process to ensure that you're able to form the trust here. So when you have multiple parties involved in it, you're able to provide a good form of trusted identity here. Similarly, you have to ensure that you're able to do role-based access control along with authentication. What it means is that different users or different entities which are part of the entire supply chain have their own control as well as the access policy they are provided with. For example, a different entity will have different responsibility and different kind of different levels of access to the system. Now, when we talk about IoT here, right, this is actually quite general applicable over IT domain as well. But here we have to make sure that this is applicable over IoT. So we have to go back to the initial problem. We had that there's a constant complexity of the IoT devices. We have multiple standards, and there's a heterogeneous protocol which exists in the IoT domain. Now, apart from that, you have to also make sure that it works over hardware device as well as the software and services which are deployed over those IoT devices. So on the devices side, for example, you want to do trusted mutual authentication or signature or multi-factor trust or RBAC, right? You can use, let's say, secure element. So for example, with a secure element, it's a hardware-based secure element. You can do all of these functionalities to ensure that your physical hardware device is not tampered with. You're able to do multi-factor-based authentication, as well as you can have role-based access control to access a hardware device. But the same thing you can also do on the software side as well. For example, on the firmware, operating system, as well as other application packages which are deployed over it. Now, that being said, when we look from the commissioning and from the deployment point of view, right, we have to make sure that the devices and network are able to have a proper lifecycle management. So proper lifecycle management means that you need to have automatic commissioning, meaning that there should be no party involved in deploying the keys. If you look from the previous examples, right, when you look through the supply chain, where you have OEMs, you have distributors, you have system indicators, right, there are multiple parties involved who are exposed with the keys, meaning that they know the internal functionalities of the system and what kind of keys are deployed. With automatic commissioning, you are able to mitigate any attacks which comes from those kind of vulnerabilities there. Similarly, with automatic keys and set updates, you are able to ensure that none of the humans or system or components are involved from a manual perspective, or at least exposed to the outside world that this particular device is deployed with this kind of keys or this kind of certificate. So what happens here is that with automatic commissioning, as with automatic keys and certificate updates, none of the parties should be aware about what kind of keys are deployed by this particular device or this particular network, as well as even the administrator should not know what kind of keys were managed. So for example, even if they're managing KMS system, right, there should not be a way for them to actually expose with the KMS system. Now, there are multiple ways to do that. There are standards like IEC 62443, ISO 27001, ISM, as well as the local Singapore TR64 based standard. Within those standards, there are a lot of discussion on automatic commissioning as well as automatic key and certificate updates. So my suggestion to you guys will be to actually go through it and to understand more about how this really works out. But apart from that, right, we have also need to look into some of the aspects like remote deployment, right? So when it comes to remote deployment, when we want to deploy devices in the field, we have to make sure that these devices, when they're deployed, there's not going to be user intervention or human intervention, right? So we have to make sure that any kind of key updates or enrollment updates, right, we have to control through the server. So typically in the system, when we see, right, an IT-based system, what we do is that there's a user sitting in front of a computer who basically do the update, right? In the case of IoT domain, we have to basically make sure that you're able to follow the lifecycle management through a remote perspective. Similarly, at the end of the lifecycle, when the devices are at the end of their own deployment, you have to make sure that you have proper policy to do device key and certificate retirement. Because what happens is that in the traditional world, when we look into IT or laptops or your cell phones, right, before you give it to your siblings, before you throw away, you typically wipe it out clean, right? But if I ask the same question in terms of, do you follow the same procedure with your IoT devices, with your CCTV camera, with your access control door locks? Maybe not, right? This is very common with other industrial control systems as well. So majority of the industry, they don't typically have the retirement process. So for example, if you want to delete the keys or retire a particular firmware, are you able to do that with the particular device? So if you're not able to do that, you have to go back to the vendor, ask them to implement that functionality. Okay, the fifth component is more towards the package vulnerabilities. Now, this is something which is a growing concern among most of the IT devices right now. So for example, the Mirai botnet was one of the biggest attacks which happened because of vulnerabilities. So for example, when you buy any IT devices or when an industry deploys their IT devices, right, they typically come with certain packages. It could be third-party open source packages, it could be third-party closed firmware packages, and so on. And over the period of time, a lot of vulnerabilities are discovered over those packages. So you have to ensure that you are able to manage those vulnerabilities. Otherwise, what happens is that any malicious user will be able to push their own, or maybe will be able to write down that vulnerability to push their own compromised firmware updates or software updates to compromise the device. Now, to mitigate that, right, the device has to make sure that it's able to download the services and firmware and software and other things like that from a trusted source. So again, it goes back to mutual authentication, meaning that you should ensure that all of the software components, all the packages are downloaded from a trusted site or trusted link. Similarly, at the end, right, you want to make sure that there should be a secure photo component as well, right? For example, you want to update the particular device because you see that particular package has been compromised or particular firmware needs to be updated for certain additional functionality reasons, right? In that case, you of course you need to make sure that you should be able to sign the firmware, make sure that the firmware is downloaded by the right user through the right admin control policies, as well as installed in the right way on the devices by verifying the who's issued or the firmware, who actually issued the command of the particular firmware update, and so on. So later on, we're going to see an example of how this should be done, but this should actually basically cover the entire lifecycle management in terms of how the commission should work, how the update should work, and how we should do the retirement process as well. Okay, now let's look at one of the examples here when it comes to role-based access control here, right? Now, this is actually quite an important process, especially when it comes to supply chain. So here we're going to see 4 different elements involved. We're going to see system administrator, we have device manufacturer, we have system operator, as well as system integrator here. So 4 different elements involved in this particular use case here. Now, that being said, let's look into how this particular process will work out, right? So you have device manufacturer, where basically programs the devices along with the signed commission certificate to the system integrator. This system integrator then performs the device deployment, and when the device is deployed, they auto-enroll with a new certificate or new keys based on how the device has been configured with, right? So again, device manufacturer provides the program devices to the system integrator install on the IoT devices with the auto-enrollment of new certificates which are generated by the devices here. Now, so this is a good process. Now, let's say there's a system operator, right? This system operator, jumping ahead, let me just go back to here. I forgot to mention one thing here is that each of the device or each of the elements here, they have their own certificates which are provided for authentication and control. So this is basically securing supply chain with certificates. So each of the elements here have a digital certificate. Each of these digital certificates mark the access control or the authentication level they're allowed to. So coming back here, right? This particular system operator, let's say when it sends a particular, let's say, operation-related commands, right? What it does is that it signs the operation command with its own certificate. Now this device, IoT device, verifies the commands based on the system operator certificate signing and sees whether this particular command has been verified or not. And since system operator has its own certificate for signing the commands, the IoT device verifies it and basically performs the operation it's supposed to. But let's say this system operator wants to do admin level commands, right? It's sending admin level operation commands, for example, doing updates, photo, or maybe deleting the keys or things like that, right? But those are admin level commands. So even if it signs it with, for the admin level commands, the IoT device is going to verify that, no, this is not signed by the admin certificate. This is signed by the operator certificate. So it's going to reject that particular command. Now, let's look at system administrator, right? So when we look at the system administrators, right, we always see that the system administrator has the full control over the system. But from a role-based access control, we have ensured that the responsibilities are distributed to different entities involved in the entire supply chain. For example, if there is an insider attack from the system administrator, right? Let's say if the system administrator wants to compromise the devices by updating with its own compromised firmware, it shouldn't be able to update it. For example, let's say the system administrator signs a firmware with his own certificate and sends to this IoT device here. What's going to happen is that the device will reject this particular firmware. The reason because it's not signed by the device manufacturer. The reason because when you have a particular firmware, the firmware needs to be signed by device manufacturer. And the admin level operation commands need to be done by system administration. So meaning that even though the system administrator has the right certificate to update the device, it doesn't have the right certificate to sign the firmware. So meaning that the IoT device is going to reject that particular firmware update request. Now, let's say the device manufacturer wants to update the device with its own firmware. So in this particular scenario, right, what happens is that although the firmware has been rightly signed by the device manufacturer, but the admin level command is not signed by the system administrator, meaning that the device manufacturer alone cannot compromise the system. So the right way of doing the update would be the device manufacturer sends the signed firmware to the system administrator. The system administrator then signs the admin commands and then sends the signed firmware to the IoT device. So what the IoT device is going to do is that, first of all, it's going to verify whether it's admin level command by verifying the authenticity and the verification of the request. So when it verifies that, then after that, it verifies whether the firmware is legit or not. So to do that, it verifies the authenticity and the signing of the firmware, which is done by the device manufacturer. Once these two conditions are met, then only after that, the FOTA is performed. So this is how a general supply chain will normally looks like. You can add more and more controls over it to ensure that you're able to add more functionalities, more redundancies, as well as you're able to distribute the liabilities and responsibility across different elements of the supply chain. By doing that, you are able to ensure that if an attack happens for God's sake, any reason, right, you're able to pinpoint the exact element who's responsible for the attack here. In the case of, let's say, the ASUS live update attack, right, you can't really say whether it was done on OEM side, whether it's done on the software side, because there are multiple parties which are involved in it. With this kind of approach, right, you're able to figure out who's the one who's responsible for the attack here. So by doing this kind of supply chain based, role-based access control for supply chain, right, you're able to figure out, pinpoint and pinpoint the attacks, as well as you're able to distribute the responsibility across various elements of supply chain. So this is my last slide. There are a lot of other companies in the market which are solving this problem. There is a lot of companies which are trying to solve the issue with digital certificates. The company which is trying to solve it without certificates as well. Especially when it comes to the Industry 4.2 aspects, you have to make sure that all the way from device manufacturer to the supply chain logistics, as well as coming back to the system integrators and the system owners, right? You have to ensure that all of this is secure. Now, there are a lot of companies which are securing different components. There are other companies which are securing whole components as well. So if you have any other questions on this, right, please do come talk to us. We'll be more than happy to actually help you and assist with this kind of cybersecurity assessment and things like that. Yeah, that will be all. Thank you.
We will now have the Q&A session with Dr. Mishra, hosted by Dr. Vivi Suhendra, Executive Director of the Singapore Cybersecurity Consortium.
Good morning, everyone. Vishram, very good to have you here. Thanks a lot for the talk. So yeah, let's us unmute you and you can start talking also. So let's see what questions we have. So the first question, what are some trends you see happening in the IoT field now or in the near future? What is your take on this? I think you should be very plugged into the IoT field, right? Yeah.
Thanks, Suvi, for hosting these questions as well, right? Okay. The first question, of course, it makes a lot of sense because people are actually asking about a lot of questions about IoT, right? Especially the field. In reality, when we talk about IoT itself, right, and people talk about future as well, right? We are seeing it right now happening, right? All the smart systems that you're seeing right now, even just looking at the, let's say, smart utilities, energy meters, water meters, and so on, right? Apart from that, the OT control systems, which are already in place, right? They are in some form connected, and we can basically say that they are like an IoT, right? Now, there are two aspects we are looking into, right? The first is more towards what's happening in the field of IoT itself is growing, and there are a lot of surveys, there's a lot of predictions that they will have like 50 billion devices by 2025 and so on, right? But more importantly, what's really happening in the field of IoT cybersecurity, right? So currently at the stage right now, even in Singapore, right, we have TR64 standard and CSA basically also launched the labeling scheme. Apart from that, if you look internationally as well, right, there are multiple standards coming in. There are multiple governments to ensure that we have a good cybersecurity mechanism to address the IoT challenge, right, or IoT security challenge. Now, if we don't address it right now, the demand is so much that in the next 5 to 10 years, we have so many IoT devices in the market that will be vulnerable to attacks. And if you don't do security by design to those systems, right, retrofitting the existing devices with new cybersecurity doesn't really work. So the way we actually look into, let's say, monitoring solution or protection solution, right, the monitoring solution alone is not sufficient. We need to make sure that we need to have protection solution around it. And that's where the standards are in. The question is more towards whether the industry is adopting those standards. So when it comes to the government side, of course, they're adopting it. They are mandating that you have to bring this standard and so on and so on. The question then goes back to the enterprise customers or the private companies, or let's say the companies which are basically adopting it, or the IoT solutions, whether it's in the industry 4.0, autonomous vehicle communications, there's plenty of domain, right? So the question is more towards those industries which are not really adopting it. And we are currently trying to make sure that there are ways to either address it in a more nominal form that we should be able to, people should be able to understand it in a very well-defined way. And that's why we also have standards which are defined in a very clear way as well. For example, when you have a high-level standard like IEC 62443, right, which is basically ICS cybersecurity standard, we also have a reduced version of the standard as well to ensure that at least we can have local adoption or small adoption, right? So currently, this is the state right now. In future, of course, we'll see more and more new standards coming in. We'll have more convergence. Of course, right now we see that the industry is quite, heterogeneous. We basically vary from one region to other region, as well as one vertical, other vertical, right? Moving forward in the future, right, is going to converge. Although there will be separation, for example, LP WAN will be separated than WAN and so on and so on. But within the LP WAN category, we will see convergence, and most likely we'll see more convergence in the security part as well. So currently, when you see a lot of cybersecurity companies which are coming in the market, they propose multiple solutions, right? We're also seeing convergence in that direction as well. I hope that basically answered the first question. Yes, right.
Yeah. So do you think it's quite realistic to expect these standards to converge,
yes.
or do you need
yes.
a push from somewhere else to get them to converge? Yes, maybe from industry side. Yeah.
Actually, you do need to push it. So especially when it comes to cybersecurity, right? Until we see an attack, people don't really move. And this is something we have seen, right? And the attacks are actually increasing day by day. So even if you don't realize it, or maybe you try to avoid it for some reason, right? One day or another, right, is going to happen. So at the end, right, it should be the industries, it should be the government, right, who have to actually drive this thing. They have to push for standards. And at the end of it, right, it will converge. Just like any other standards, right, they normally converge, it will converge.
Okay. Yeah, I believe you're also working closely with government and also the industry, so probably you could also help to bridge all this convergence to happen. Yeah. Okay. So let's move on. Yeah. Okay. So let's move on to the next question. What would you propose to speed up the process of making Singapore a real smart city, where gardeners can remotely water the plants and parks? So probably we've been hearing about the smart city, smart nation for quite some years. Of course, this is not an easy process, and many things have to come together. So probably this is somebody who's feeling that we need to probably speed it up since it's been a while.
Okay. To address this, right, I think we are getting there based on all the initiatives we have seen, especially with Singapore government, right? I mean, there are a lot of initiatives right now, especially in terms of moving towards smartness, right? Especially, let's say, if you look towards even the energy meters, water meters, and utility side, we are getting there. It may take some time, but we are getting there. The question is more towards how to speed up that process, right? Unfortunately, I would say there's no real way to speed it up. The only way we can speed it up is by adopting it in a way where we have to invest more money. For example, when we think about cybersecurity, right, especially from the production point of view, right, we always think of solution first, cybersecurity as later, right? So for example, if you have two solution provider, one with additional security and a lot of other components, right, of course the solution is going to be costly, right? For you to decide, right, you try to actually use a solution which is cheaper, is budget friendly, and it could be easily deployed, and it could be easily used and flexible enough for you to work in according to your silo operation, that whatever you have, right? So but when you choose to go with that kind of let's say, solution, right? What happens is that it's fast, it's quick, but you will suffer in the long run. Your solution is not secure. You're not able to interoperate in a secure way with other solutions, right? Because when you talk about real smart city, right, there needs to be interconnectivity. Just having one solution in silo is not really smart enough. So I think the second part was more towards one question of where gardeners can remotely water the plants at end parks, right? I think that can be easily achieved, but the question is more towards what level of connectivity you're looking into. For example, if you simply want to have a silo solution to let's say remotely water the end park, that's doable. But do you really want to make it more smart where it should be automated? It should depend upon the rain, or whether if there's a rain, you don't really have to water the park. So when you add more connected elements in it, right, it becomes more and more complex. So, for example, right, if you simply have a manual control, a remote control to basically turn on, turn off thing, right, it's fine. But let's say when you add sensors to monitor certain things and then you actuate based on the results of those sensors, right, you're adding more control elements. And there you have to do design consideration. You have to look at the vulnerabilities which comes out of that. So yeah, it is possible, but you have to make sure that you are looking at the entire aspects of it. And to be honest, based on what we've seen, Singapore government is really pushing hard in that direction. So when we talk about real smart city, it's really pushing in that direction.
Yeah, so we can be fast, but we cannot rush something like that.
We cannot rush these things. We cannot.
Yeah. Okay, so moving on, there's a question about what are your thoughts around detection of firmware backdoors?
Which question is this? Oh, sorry.
Yeah. So,
what are the thoughts about detection from firmware backdoors, right? This is actually an interesting challenge, and there's no easy way of doing it. Okay. First of all, when we look into, let's say, source code review, right, and that's a very common way of doing it. Even the cybersecurity level, the labeling scheme level 3 also demands for it. The IMA requirements, as well as any FIPS level requirement and EL requirement, the common criteria, right? At certain level, they basically go through the source code review. But let's say if you don't do source code review, right? Let's say you simply go to any firmware which we downloaded from, let's say, any solution that you're using, right? You download from their website, you're basically trying to use it, right? In a nutshell, there's no direct way of figuring out whether it's a backdoor or not. The reason why is because in certain cases, what happens is that that particular backdoor will remain dormant for quite amount of time. For example, it may remain dormant for 1 month, 2 months, 1 year, or something like that, right? And it can become active at any point of time. So you won't really notice that. The only way to do is that you try to bring the firmware inside a virtual machine. Put that in a virtual machine. You basically do a virtual test on the virtual machine by doing all the clock test analysis, figuring out if there's any code which is looking into the code-based or timer-based ticks. And on top of that, you can look at any of the registers which is trying to access where that particular register is based on either any activation in later future, any subroutine which is not really went through, or any other functions which are not invoked through, right? So based on that virtual machine-based environment, right, you can actually figure it out. But it has to actually go through that particular virtual machine-based test. And there are a lot of companies which are doing that right now. So there are some companies where you can pass your firmware and they basically, along with the platform it has run onto, right, they can do a bunch of tests on that to ensure that whether they are backdoors or not. But as a consumer itself, right, if you don't have that kind of virtual machine, if you don't really have experience on that, it becomes very problematic. So based on some of the information that we know right now, there are companies which are coming with a cloud-based solution where you can upload the firmware along with the platform, and they can tell you which functions are built inside the firmware. It can tell you, for example, that particular firmware is using this function, this library, whether that library has been compromised or not. And it can also tell you, for example, these functions will be invoked at this point of time, and so on, so on. And it can also tell you, for example, which functions are going to invoke certain ports or not, or whether it's going to open up a socket connections or socket server on your particular firmware. So by doing that, of course, you can get up to a certain level, but it's not 100% proof. So you can use those solution to, counteract certain vulnerabilities and figure out those attacks, but it's not 100%. It's not a 100% proof solution.
Yeah, I think we know there's never 100% guarantee in this. Sure. So, okay, there's another question here. Besides the technical challenges that you described about the challenges in the supply chain, so how do you see the ecosystem adoption of identity at the supply chain level? Is it
okay, so when it comes to IT side, right, IT systems, this is actually well adopted. You have ISO 28000 as a standard. You have IC 62443-1-4 as -2-1, right? So these are some of the standards which basically identify that you need to actually have these kind of trusted identity in place. But when it comes to IoT, right, it's still in infancy stage. The reason because we don't really have a well-defined standard itself first, right? In the IT equipment, you have well-defined standards. For example, the devices will be based on IPv4, IPv6 protocols. They will have firewall. They have, so they are well-defined structure for that, right? But in IoT, you have 35 communication protocols. You have more than 15 microprocessor standards which are targeting different architectures, right? So it becomes very hard to figure out what kind of standards they need to adopt in, right? For example, if you use LP-WAN solution, right, the key management solution, the IT solutions are different. When you go towards, let's say, LP-WAN, which is based on, let's say, BAN network or WAN network, right, it's different. When you go towards, let's say, personal area network based on, let's say, Bluetooth, ZigBee, and so on, it's different, right? So depending upon which solution you're looking into, the INT solution varies. And when you look at the supply chain, right, many of many of the parties which are involved in between supply chain, right, they're not really aware about what sort of technologies are really involved in. For example, if you go to a distributor, right, and we ask them, oh, we're looking for an IoT gateway with, let's say, ZigBee and Bluetooth solution, right? They will always give you the gateway, right? But when you don't really want to talk about, let's say, ZigBee or Bluetooth solution, they have no clue about it. They simply say, oh, the gateway comes with this kind of solution, just use it, right? So we are not there yet when it comes to IoT, especially in the supply chain. In terms of adoption, we are moving there, especially with new attacks coming in. We have seen a lot of supply chain attacks happening right now in the market. So what's happening right now is that the consumer are going back to the system integrators, system integrators going back to the distributor, the distributor going back to the manufacturers, and so on, right? So it's getting there, but it will take at least another 4 to 5 years to have a well-defined structure for the entire supply chain-based security. So it will take at least 4 to 5 years. So I hope that I answered that particular question.
Yeah, unfortunately, we cannot get the audience to speak to us. But yeah. Okay, so let's move on. There's this interesting question. What is the question you are most tired of hearing on IoT security, and what would you like to say about it so you never have to answer it again? I don't think never, but at least, you can say it once. And
there are actually two things we normally hear about it. The first thing is that, can you provide an IoT security solution which can be deployed to existing infrastructure? And this is actually very common, right? Because we are talking about brownfield, right? So you already have commercially off the solution. We bought it from China, Taiwan, a lot of other countries, and you want to secure it, right? There's no way to secure it. I'll be honest with everyone. So there is a distinction between protection solution and monitoring solution. These are very different. People say that, oh, but these are the companies which are securing the solution which is already deployed. No, they're not securing it. They are monitoring it. They can put a firewall in front of it. They can monitor it. They can figure out whether there's an attack happening or not. But anything in between, right? When the devices don't have encryption capabilities, right? You can't really put encryption capability in front of it. That's impossible. You have to update the firmware, or you have to add additional devices in between. Without doing that, there's no solution which can target that particular protection feature. So when you're looking at a solution, right, make sure that what you're looking for, are you looking for protection solution, or are you looking for monitoring solution? So monitoring solution or retrofitting solutions don't really provide protection. For example, there are a lot of other companies in the market which are targeting monitoring solution. They basically say that, well, we provide IoT cybersecurity and so on, right? Be very careful. They provide gateways, they provide firewalls, which basically provide monitoring capabilities to the devices behind that particular firewall. And in a sense, they do provide cybersecurity protection, but not the cryptographic protection that we normally talk about. For example, they don't provide mutual authentication. They don't provide session key encryptions and even the encryption capabilities. So the devices which are already deployed, right, they'll still be talking in plain text language. So attackers can still sniff onto the network. So there's literally no way of doing that. So that is something that really bothers me when people actually ask me this question, okay, can your solution or can other solution retrofit into this? No, it doesn't work like that. If you really want to do it, you have to do security by design. You have to put the solution inside the devices. It needs to really go on the manufactured side. What you can really do on the existing network is that you can put monitoring solution. It's not 100% foolproof, but it adds additional layer of security. So that's the first thing that we really want to make sure that the people really understand it. Protection versus monitoring, right? The second is more towards when people ask about how do we want to secure our solution. So you see, IoT security is not just one problem. It consists of multiple problems. So if you look into my slide, right, I think slide 2 or slide 3, I just mentioned about different geos, right? We have devices, gateways, the communication protocol, and the cloud. Within that, we have multiple problems that we saw, right? Not a single, one single security company cannot solve all the problems. So you have to work with everyone to ensure that that particular problem could be addressed. So if you come to us and say that, oh, can you actually address all of this? No, we can't. Nobody can. You have to work with multiple cybersecurity companies to actually address that particular problem, right? It's not like just one solution for all. It doesn't work like that. Yeah.
Yeah, okay. So, yeah, I hope that helps you in avoiding having to answer the same questions. Yeah. Okay, a question just come in. Let's take a look at this. What are your views on drive-by hacking threat on IoT devices?
Okay, so when we talk about drive-by, right? So okay, so first of all, I need to understand what is the meaning of drive-by here. So what I understand by drive-by is that normally there are two kinds of attacks we are seeing right now. The first kind of attack is where you see an attack which happens in the vicinity, on the nearby, right? So for example, let's say you have a solution deployed inside an industry, you put a drone inside it, and you're able to basically do a remote attacks on it, right? And those attacks are somewhat not, I mean, how should I say? They're basically attacking on the vulnerabilities which exist on the system. So to target that, you have to basically patch the system to ensure that you're able to address the vulnerabilities which exist on the particular, let's say, firmware or the operations also, or the OS itself, right? But on top of that, you also need to make sure that you are not leaking the network outside your zone. For example, let's say if you have Wi-Fi inside your house, right? And I'm pretty sure that nobody here controls what is the EIRP or the output of the Wi-Fi they're using within the router. So it's, for example, right, you put a Wi-Fi router inside your house, right? It's broadcasting the network, and your neighbors can also see that, and the neighbors behind that can also see that, right? So when you try to set up a network, you also need to set up the power in such a way that the network should be visible within your own house. It should not be visible outside it. The other meaning of the drive-by, which I take from this particular consideration, is that especially the attacks which are happening based on, let's say, for example, the vulnerabilities which are coming in, right? So especially in that kind of attack, you have to make sure that the solution which are deployed, right, make sure that they are patched and up to date. For example, the two attacks which I described in the talk, right? For example, Operation Shadow Hammer and the Lemon Deck, right? Apart from that, there are a lot of other attacks as well. Those attacks happen because the systems were not patched. Similarly, one of the most famous attack which happened on the IoT devices was Mirai botnet. I think during the entire Go and SIC did, right, we heard about the Mirai botnet a lot. I mean, millions of CCTV cameras were compromised. Those attacks happened because the systems were not patched. And of course, it's a very common problem. I'm pretty sure that most of the people who have CCTV cameras inside their houses, right, or even in their offices, they're not patched. If they are exposed over the internet, right, then people can, compromise the system based on the vulnerabilities which are already existing on the systems. They will be able to load their own firmware. They'll be able to do code execution and things like that. So we need to make sure that systems are always updated. They're always patched. This is something which is highly recommended for everyone.
Yeah, thanks for that. Just nice. I think we need to wrap up here.
Yeah.
So, yeah, thanks once again, Vishram, for the discussion. Thanks to you all in the audience for sending in your questions. I hope you found it answering your concerns. So I hope you in the audience will join me again this afternoon for discussions after the tutorial. Yeah. Okay, Vishram.
Thank you. Thank you, everyone, and thank you, SSCW, for hosting me here as well. And thank you for the opportunity to talk about especially with the supply chain cybersecurity. It's important. If you guys have any more questions, feel free to drop me an email. I'll be happy to talk about it. And thank you, Vivi, for hosting this entire questionnaire as well. Thank you.
Yeah, very good to have you here.
And have a nice SSCW session. I think it's going to be end of this week, but yeah.
Great. Yeah, I think we are the last. Okay, great. See you, everyone.
Thank you.
Thank you, Dr. Mishra, for the insightful session. We will now take a break for lunch. The program will resume at 1 p.m. with the research tutorial on deep dive into IoT security and IoT protocol vulnerabilities. Enjoy your lunch and see you back here at 1 p.m. Ladies and gentlemen, welcome back to the Cybersecurity R&D workshop. This afternoon, we are honored to have Assistant Professor Sudipta Chattopadhyay and Mr. Matthias Garbellini to deliver the research tutorial on deep dive into IoT security and IoT protocol vulnerabilities. Assistant Professor Sudipta Chattopadhyay is an assistant professor at the Singapore University of Technology and Design. He has extensive experience in testing and analysis of non-functional software properties such as performance and security. His research on wireless security testing has received global attention from regulatory agencies in Singapore and US. Together with his group, his research has led to more than 20 common vulnerability exposures in Wi-Fi and BLE implementations in the wild. Mr. Matthias Garbellini is a PhD student at the Singapore University of Technology and Design. His research interests include wireless security, cyber-physical systems, IoTs, and embedded systems. His recent research has discovered Swain-Tooth and other critical wireless protocol implementation vulnerabilities. The speakers will take questions at the end of the talk. Professor Chattopadhyay and Mr. Garbellini, please.
In this tutorial, we will present basic things that need to be taken care of for IoT security, and then we will discuss in details about IoT protocol vulnerabilities. Before we go into the details, I just want to give you some sort of outline what we are going to present in this tutorial. So in the beginning, what we will do, we will present some basic stuff about IoT architecture and its unique characteristics. We will also talk about unique security challenges that appear in the case of Internet of Things. And we will discuss some state of the art in testing IoT protocols. We will see that there hasn't been much work done and a lot needs to be done in this area, in fact. After that, we will discuss some of the recent as well as some of the classic wireless protocol vulnerabilities that have been discovered over the years. Especially, we'll discuss Wi-Fi and Bluetooth protocol vulnerabilities. Next, we will discuss how these vulnerabilities actually can be discovered, because these vulnerabilities are quite complex and require some special mechanism to test, to find these vulnerabilities. Now I will hand it over to Matthews to talk about basic IoT architecture and its security challenges.
Okay, so starting with the introduction, we look how the general IoT system is organized. So we have this concept of using IoT on many types of applications, and this means that we are using IoT devices for not only tiny things but also for big things, and this is also for the industrial field. So automation, for security cameras, for example, for environmental sensors. So many applications. And the interesting thing is that depending on the type of the device, it extends not to only one type of device, but an entire ecosystem. And this means that for one device to connect to the internet, there is many other devices there communicating. And of course, security is crucial from the first device until the end device, the one that connects to the internet. In this case, it's common to have an IoT architecture, the gateways, to make the bridge between the device on the field to the connectivity on the cloud. So as important features of IoT and why it's so relevant nowadays is because of its connectivity, and there's also some trade-off of this connectivity. So although it's easy to make a connection between multiple devices, on even when you're using your smartphone, which can be considered IoT device depending on the context you're using. And there are plenty of good things about using connected devices. So by start, these devices are small. They consume low power, right? But another point is that they may involve many different technologies, which relies on certain set of standards and also implementation. And all of this needs to be secured. So if you look about what could be the disadvantages, so it's mostly its complexity, and because it's complexity, there comes some challenge in regards to the how difficult it is to implement a complete secure system. So in these terms, we have the implications on privacy and also overall security on when two devices are communicating. But the current focus on this work is mostly on the security part, on what are the different types of architectures on IoT that can be targeted in particularly in regards to wireless implementation. So if we expand here tomorrow the communication between two devices, we can also classify by the types of IoT networks. And the mostly common devices that we can buy nowadays are communicating via these two. There's certain popular two types of networks here. So we have this wide area network, which is common for Wi-Fi, and the local area network, which the area is reduced. So it's common that we have, for example, certain devices such as smartphone operating on local area network, and your smartphone can also operate in wide area network, right? Because you can also communicate with the tower, for example. So, and also there is certain devices that are specifically built for multiple types of these technologies, or just one. They can change depending. So the complexity on their implementations is even higher in this sense. So when we talk about comparing with the web, then we can make a sense of why IoT is different in a sense and why the implementation needs to be different. So we have these smart devices, and then later we usually connect IoT device to a gateway. So even your smartphone you can think as a as an endpoint device, and then it connects to your Wi-Fi gateway, and then to a cloud service, right? So on the right side here, we have the OZ diagram of the layers of the network, and starting by the physical layer, go all the way to the presentation layer on these two types of devices here. And you see here that we have the data link layer. Now, this layer is really important because it's the first layer that has, you can think of the first messages passing over the air. So it's all bytes, and it's this layer that will have the first protocol definitions on how the two devices are communicating. The network layer is responsible to route this device, but sometimes it can be present together in data link layer depending on the protocol. And lastly, we have the cloud. So if you're talking about securing IoT ecosystem, there is all these types of particularities where we are focusing the security. So there is the IoT network itself, but also all the connectivity to the internet. So, and going further, what we have here is, of course, we can dissect each layers to different sorts of parts of protocols. So for normal, starting by the cloud part, which has the connectivity between the gateway and the cloud, we have the normal internet protocol. So it's familiar to know this protocol such as TCP, TLS, HTTP, IPv6, which is the data link layer, the common data link layer for wired networks. But also we have the when making the comparison with the Internet of Things with the Stein device, we have different sets of protocols for the same layers here. So for example, because these devices are constrained, the implementation needs to be lightweight. And with this, we have different protocols that are their sole purpose is to reduce the communication overhead between devices. So they do not rely on a powerful software or much more tested software that is usually present on gateways or in generally cloud infrastructure. So here we have a common protocol such as 6LoWPAN, which is this showing here, the data link layer here. And then UDP is the same, but then we have maybe different other protocols in the higher level, such as DTLS, CoAP, or web objects. And going further, but then the IoT field per se is complex, and we have different types of devices, different types of hardware, different types of protocols. So if you look in an overall view on how it looks fitted all together, you can see a block like this. So in the physical layer, when we talk about different wireless technologies, we have this IEEE 802.15.4, which is part of the 6LoWPAN. Then we have Bluetooth, Wi-Fi, NFC, 3GPP. These are common technology that we are used for. And on top of that, we have these different protocols, which are complex. It's not a single case that vulnerabilities may explore not only these layers that we are used, such as this TCP, UDP, but also the lower level protocol implementation present on these wireless technologies. So as an example, if you look here on how this ecosystem is organized, we have these different protocols for the higher level. So if you talk about messages being exchanged between the gateway and the cloud, we have protocols focused on different fields. So DDS, for example, uses UDP for the transport, right? Other protocols may use TCP. So depends on the type of technology, and also their model is different. They not only their speed, but their latency is different, and each one has its different security mechanism. But mostly, if you're talking about general web, they mostly use TLS or some variant which is common, known already to normal web. However, they're kind of fitted to be more light when implemented on a different, more lightweight gateway, for example. But it's common that we have the standard for each one. For each one of these IoT protocols, we have the specification. They specify each one of these characteristics of each device, right? And of course, the difficult part is how to implement this correctly, right? And how to test this implementation correctly so we don't have some hole on the implementation. And on the device side, on the wireless side, the endpoint IoT device. We have more a more spread technology field with a diverse set of wireless technologies. So for the standard, here on the table, we show like different types of standards for different types of technologies. So IEEE is the common one, 3GPP for smartphone networks. Then we have the different ones, which is not that common, but waveless, +7. LoRa is particularly popular right now, so it's a network that is supposed to cover a lot of area. And then we have the specification, which then specifies a bit more what are the protocols the message is being exchanged, right? It's common that one device may employ many types of wireless networks, which makes things even more complex, right? So then for the implementation, it's complex in the sense that we do not only care about the hardware itself, but we also have to care about the radio also. So the hardware must cope with a specific type of radio implementation, which sometimes the way that vendors implement this technology may be more complex than others. It may lead to different types of vulnerabilities. So here I show the general device architecture. So if we're talking about IoT sensor, a smart tracker, a smart bulb, generally they employ what we call a system on chip or a microcontroller. And then we have the normal software implementation inside, which we have the application, the threads, and so on. And then we have also the hardware, which must be capable to support many of these IoT communication, right? So, but then we can classify the IoT devices a too broad term. And if I try to explore what kind of device to secure, we need to understand what type of device is being used in IoT network. So we can think that we have, for example, 3 types of these devices. We have the embedded device. So for devices that run usually a full-blown Linux distribution, like such as this Raspberry Pi, it's usual that they are like these high-end IoT devices. Then you have the system on chip. So these are like small modules that some products employ. With inside, they may have different components. And then we have the microcontrollers, which is just a single package and has everything inside to communicate with other devices. So it's general that this device has a radio integrated there, and you program directly to the board. And so, but what is the difference, right? So the difference is that for each type of device, they employ certain levels of security. And we can think that for low-end IoT devices, they use so this shows like some example of some devices that employ this low end. So Arduino is one example, but it's not an IoT device per se. You generally need to employ with a different projects to become a full-blown IoT device. Another popular devices is an NRF51, which is a microcontroller which has integrated Bluetooth. So in terms of security, it does not have full-blown security. For example, does not have address sanitizer, which is common for when you try to secure application to not to be vulnerable against the buffer overflow attacks, for example. And they may or may not have support for cryptography. They may be limited in terms that the vendor does offer some support for cryptography, but it may be completely on software, for example. So it may be only used for lightweight communication protocols. Then you have the middle end, which is a bit more expensive, but employ, for example, hardware cryptography, has also more capability to employ more complex applications. And then we go to the high end. So the high end, you can go all the way from a simple Raspberry Pi, a Linux standalone board, to our own smartphone. So then the security there is complete because it runs a full-blown operational system. So then we start. What is the summary of the security challenges? With all those types of different technologies, all different types of hardware devices, we need to focus on the design and implementations. These are the things that must be impeccable on different IoT, particularly if you're talking about industrial. And testing is also really difficult with these devices. generally the wireless by itself is not common as wired networks, and it's not easy to test because the equipments are expensive. So the security, the easiness of testing security of these IoT devices depends on how accessible these equipments are. Usually they are expensive. And then if you talk about how to secure devices, usually they do not employ the same software techniques which is present on normal wired networks. So this is also another challenge. And then one question that arises with all this is, it's possible to detect vulnerabilities systematically. So one of the challenges is that nowadays we are seeing a lot of different vulnerabilities for Wi-Fi, Bluetooth, for example, which are common networks for IoT. And there could be some way to better test this type of networks against this sort of vulnerabilities. And here I just shown the stacks or how they're organized. So for each vulnerability, they affect different layers of the protocol. So you see, more layers a certain technology has, more complex it is. And it may affect the software supply chain. So there is an issue that the vendor may rely on a different vendor, which is, for example, handling only the implementation. And this is a bit difficult to secure. So here I show like more or less how the architecture of an IoT device works in terms of the vendor. So we have here the how internally it's designed, the wireless semiconductor. So we have generally the wireless IP vendor, which sells the technology itself, the design. Then the semiconductor vendor, which is responsible for the microchip itself, that employs its all other parts of the microcontroller. Also the wireless SDK API, which is supposed to control the radio from the wireless IP vendor. And lastly, there's the product vendor, which then uses all of this stack to then create a product. Then we have the firmware, which then makes the IoT product. And you need to secure everything. So it's difficult to secure each one of these layers. And each one of these layers start from the wireless stack. Starting from the standard, which is the one that if there is some flaw, is the one that most affect all of the devices using the technology. Then we have the wireless stack, which affects all the IoT devices used by that semiconductor vendor. Then if the SDK API has some vulnerability, it may affect some products using that some feature of that IoT technology. And then lastly, we have the vulnerability specific to a certain product, which only affect a certain range of products, which is the least impactful. Then it shows two different ways to organize the IoT product in a way that may change how security is seen on a certain project. So it's common, for example, here showing as example Bluetooth. Sometimes some products may employ a separation between the wireless controller and the host system. So to the right here is an example of how your smartphone works. Usually you have the operational system as the host system, and then the controller, which employs the wireless stack. So if there is a certain vulnerability on the wireless, on the controller itself, it may or may not impact directly the host system. So there is an isolation here. So even if the controller, for example, crashes or restarts, the host system will still be okay. And yeah, showing these two targets here. So another common approach for cheaper devices, for example, is smartwatches or some smart trackers. Usually the product vendors employ a single solution. So they may develop their product in one single package. The firmware contain the wireless implementation. And in this case, of course, the cost is lower, but there is only a single point of failure. So if there is a vulnerability on any of these stacks, then it's critical. The product is mostly always affected. And here, to summarize, then what are the challenges? So here it shows why is it difficult to test wireless. So usually the timings are quite low. So 10 microseconds, usually the timing between sending a message from one device to another and then to another. So it's difficult to test this in real time without further modifications on the firmware itself. And of course, the protocols are complex, so there are many states there. And then if you're trying to test the implementation over the air, it's not easy to get metrics or to know how the device is behaving internally. And then, of course, there is also the way that the wireless stack is either saved to the firmware itself, or some vendors may employ to the read-only memory, which cannot be modified and is even difficult to patch if there is some vulnerability. Here it shows more or less why the system, nowadays the IoT field is complex. So many types of platforms, software platforms for high-end IoTs, also for low, mid-end IoTs, and all of this needs to be secured. And here shows the state of the art. So we have different ways to test nowadays the IoT. So we have fuzzing, which is testing with random messages. The compliance testing, if we talk about only the standard and certain types of implementation, and the static dynamic analysis, which is to test the IoT implementation, given that you have the source code to analyze to detect some flaw. And the thing is to notice that if you talk about fuzzing and particularly testing the wireless stack, there's not much work on this. So because it's complex. And here's some tools. Usually when we're testing some product, there's tools to perform manual testing. So Wireshark to just analyze the protocol. Shodan, which you can search many connected IoT devices. And sometimes you may find vulnerable devices just by searching and trying to connect to them. SCAP is just a library which researchers use to snip some and then some packet and send it back to try some attack. We also have some works on the automatic testing. So Pennyot is one example of with a certain bench of tools to do penetration tests on wireless IoT networks. Then have the IoT app analysis, and this is important because there is a certain separation between wireless testing for IoT device and also mobile testing. And there are certain works that test specifically IoT apps for mobile applications. We have one for machine-to-machine conformance testing tool. And this is for static analysis. So certain compiler vendors may employ certain mechanisms to validate your code against certain mistakes. And lastly, vendors of open source projects, they employ this continuous integration to do manual testing, which is susceptible to errors, but is still widely deployed. And in summary, we have this certain fuzzing tool. So if you're talking only about fuzzing, there is a certain scarce of testing wireless tools. And here we have a summary of tools and the feature support for Bluetooth and for Wi-Fi. But you can see that mostly they are test case or random. The dynamic has some variations there, but is mostly sending messages to the other device in expectation that sending a wrong message will cause a certain crash. And the only one that is most recent and does more work for Bluetooth Classic is this Frankenstein, which is coverage guided. So the only thing is that it tries to test the firmware itself against certain vulnerabilities by employing certain emulation framework there. For Wi-Fi, still there's not much work there in terms of smart fuzzing or equivalent to what we have in software testing. So now I hand over to Sudipta.
Thank you, Matthews. Now I will go and discuss some examples of protocol vulnerabilities that have been discovered over several years. So let me first start with the vulnerabilities that have been discovered in Wi-Fi protocols. So one of the most critical and very popular vulnerability that was discovered in 2017 was called crack. And now in this slide, you can actually see many figures, but let me first explain slowly what are happening in this slide actually. So on this corner, you see this is kind of the state machine for Wi-Fi protocol. So kind of capture how the Wi-Fi protocol behave. So we will actually explain to you in a bit more detail when we discuss how to discover the vulnerabilities. But let's, for the time being, assume that this is how the Wi-Fi protocol behave, and you can represent it as a state machine. What you see here is kind of a snapshot of messages being exchanged, which is pertinent to the crack vulnerability. And here you see in this figure, this shows the Wi-Fi key hierarchy. So Wi-Fi has, in the protocol, there are many types of keys. And basically this crack vulnerability compromised this GTK and PTK. So how does this happen? So in Wi-Fi, one of the most important state is four-way handshake, as you see here. And these messages, the messages that are exchanged in the handshake state are these four messages: message 1, 2, 3, and 4. And you see that message 1, or basically the handshake, is initiated by the access point. So what happens here in the crack vulnerability? So after this four-way handshake happens, so people can actually encrypt the data using the key that has been agreed upon. However, it was found that, let's say you have a malicious access point. So obviously, if you have a benign access point which is implementing the Wi-Fi protocol perfectly, this will not come. But let's assume you have a malicious access point. What it does, it basically retransmits message 3. So, well, of course, message 3 should not be sent here. It was actually already sent here, and the handshake is complete. But nevertheless, since this one is malicious, it sent message 3 here. And according to standard, it is allowed. So this is a compliant behavior. And what it does, according to the Wi-Fi standard, it in fact restart a certain field, which is called nonce. So nonce, you can think of something like a sequence number. So when you communicate packets in the protocol, each one of them has sequence number. And that's very important for security, because if you could actually allow restarting or resetting this sequence number, then you know it is possible to perform a replay attack. And what is a replay attack? For example, you could hold up a packet for a certain time, and then you could replay the packet. It is not possible because, in general, because you have this unique sequence number. However, it is possible in this attack because the sequence number is reset. So you are starting the sequence number from some value which was actually occurred much before. Okay. Now, well, of course, this is how the security can be compromised. You could perform this replay attack. Now, it is important to know that this vulnerability is actually a design level vulnerability. So this, in fact, comes in the Wi-Fi protocol standard. So this is not like in a specific implementation level. So in general, anyone who implements Wi-Fi standard before this vulnerability was discovered was in fact mostly vulnerable to this crack attack. So next, what I'm going to discuss something called Dragon's layer, and this is not a design layer. This is in fact a implementation level vulnerability. So similarly, I show you here Wi-Fi states that that is pertinent to the behavior of the Wi-Fi protocol. Here I show the messages exchange which is relevant to expose this Dragon's layer vulnerability. So this Dragon's layer, in fact, appears in the EAP, the enterprise state in the Wi-Fi. So this Wi-Fi enterprise state. So what happens? So you usually exchange this type of standard messages. So you request the identity and the client can respond. And similarly, then there are several challenge messages that are exchanged between the access point and the client. What happens is that in this implementation level vulnerability, if you could send a EAP challenge message with a malform field. So what does it mean by malform? So you change certain field where which is not like what it's supposed to be. And in fact, this particular field that you change is something related to ECC. So ECC is electric curve cryptography. So if you change certain field related to the elliptic curve cryptography, it turns out that the client still accepts that particular message. And in fact, it proceeds to establish the connection. Now, why it is vulnerable? So you can think of, these fields are actually quite important, and this is relevant to security. So you can think of, let's say, you try to connect with a device that requires certain password, but you don't know the password. So this kind of vulnerability, you can think of something like, even if you don't know the password and you just send some random password without knowing the password, it still allow you to connect. So that's basically the implication of this vulnerability. But it of course appears only if your device implement this enterprise Wi-Fi enterprise thing. So now let me go through some of the some more implementation level vulnerabilities. So those which were discovered through our research as well. So just to remind you a certain thing. So by this time, you might have an idea that even though this example that I show you, this vulnerabilities example, these are not easy to find. It's not like someone just very quickly find, just read the standard or look at the implementation and they can find this thing. So it requires quite a bit of extensive effort, in fact, to find this type of issues. So be it at implementation level or design level, it requires a very rigorous study of the standard as well as the implementation. So here is another example which appears in a device called ESP8266. So ESP8266 is a very popular IoT device. In fact, if someone is doing any classroom type of IoT project, this is a very typical IoT device to use, and microcontroller, because it has the Wi-Fi capability. It's a very wide community, and it has been very popular for several years. And it's also widely used in relatively cheap IoT devices to provide Wi-Fi connectivity. So now, just to remind you, so this is again showing the handshake portion of the Wi-Fi. So handshake is complete, so no problem here. So this is in fact a simple vulnerability as it appears. So what happens is that if you send a malformed frame, which is basically a malformed beacon frame, and this specific malformation is conducted if you change the length of the frame. So you change the length from what it is expected to be, and in that case, this malformed frame actually can crash the client. This vulnerability, although I show it like this, in fact, this can appear in any state. So this is just an example to crash the device using a malformed beacon frame. So let me take the next example. So here, what we have, this is actually a little bit before, as you see. So not the handshake yet. So initially, what you do, you have this probe request and probe response authentication and association messages when you are trying to establish an Wi-Fi connection. And then what you do when you move to this PMK, so PMK is one of the key that need to be exchanged between the client and the access point. So what we do here, so usually after this identity request and response, a benign access point, it will in fact send a EAP challenge message. But since this access point is malformed, it's a malicious one, what we could do, of course, we can send malformed messages as well. And instead of sending an EAP challenge message, if we send an EAP success message, we can crash this particular device. So of course, if you're thinking of the Wi-Fi standard, so they clearly mention that if EAP success is sent before an EAP challenge message, this message should be discarded. So the normal behavior is to discard the packet. However, in this case, the implementation does not properly handle, and this device in fact crash. So you can think of this thing is not easy to find, because we need someone needs to find this exact message to send to crash this particular device. So we will talk about later how this thing can be found automatically. These are just some examples to show you how difficult and how deep these vulnerabilities can be. So the last one is the most serious one that I want to discuss, is called zero PMK installation in the same device. And previous one that you saw were actually crashing the device. So crashing, of course, you can think of like a denial of service attack. So you continuously restart the device that you are crashing. But of course, it could be more serious. In fact, if you kind of reverse engineer the code and launch some sort of remote code execution. However, this particular vulnerability on zero PMK installation, it allows a complete hijacking of the device. How does it happen? So again, this is the same messages that you saw in the last slide. So here we are exchanging the messages in the EAP state of the Wi-Fi. So we have a request response, and here the EAP request response is complete. And in general, when the request is successfully completed, this access point should send a EAP success message. But since the access point is malicious, so what we can do, instead of sending an EAP success, we deliberately send an EAP failed message. So what happens now, according to the standard, or what should have happened, it should not even proceed to the handshake state at all. So usually it should stop here. Nonetheless, it actually proceeded to the four-way handshake state. Now this is still okay, so far it's still okay because the key has already been exchanged, and you know, if you use a proper key, this will still be secure. But now what we try to do, we in fact see that this can actually proceed to the handshake state, and the access point being malicious, we can send another redundant packet, which is the message 1, initiating the handshake message. And as it turns out that the client in fact reply here instead of completely ignoring the EAP fail message. And what happens now is the most serious one. So it in fact could not find the pairwise master key, and in fact it drops to use a 0 pairwise master key, which is the default value. So you can think of, if you are writing the code where the pairwise master key is written as a global variable, and global variable are usually initialized to 0. So what typically, or most likely what happened here, since this stage failed, even though it proceeded to the four-way handshake state, so it could actually, instead of using a proper PMK, it goes to use the default value, and the default value is 0. And you can imagine, if the default PMK is 0, you can completely read and encrypt and decrypt the messages using this 0 PMK. So this, in fact, when this happens, the device is completely connected and controlled by this malicious access point. So this is a complete hijacking as compared to the previous one, which can only restart the device. So what all it requires is to send an EAP fail message before the legitimate access point send an EAP success message. And this can also bypass all these keys in the key hierarchy for Wi-Fi. Okay, so now that we have discussed some Wi-Fi protocol vulnerabilities, so let's move on to some examples for Bluetooth protocol vulnerabilities. So in Bluetooth, as it turns out, that situation is no better. So there has been many vulnerabilities that have been discovered over the years. So this is one of the earlier vulnerabilities, which was called bleeding bit. And this is, again, when I'm talking about the vulnerabilities, it might be either at the level of design or it might be at the level of implementation. So this particular vulnerability is at the level of implementation. So what happened, and this appeared in a specific type of Texas Instrument device. What happened is that, as we were talking about malformed frame, so this attacker who launched the attack, as you know, when you have Bluetooth device, it in fact sends this advertisement. So they send a malformed advertisement frame to in fact crash the device. But they go ahead, so not just to crash, it also reverse engineer, and it launched the remote code execution in certain in Cisco access point as well. So this was like a more manual approach to conduct this attack. So they found that this particular malformed advertisement frame can actually crash the device, and then you had to do a lot of work to launch the attack for remote code execution. The main reason for the attack appears is because of a heap buffer overflow that appeared in the link layer. Here, something is worth mentioning. If you are trying to test a Bluetooth protocol implementation from the user space, you in fact do not have much control over this link layer packet. So it is extremely difficult, and in fact, before some of the work happened recently, it was impossible to actually discover this type of vulnerabilities if you just have a user level fuzzer that is trying to fuzz, because you cannot control these link layer packets. And it also shows that why it is important to discover vulnerabilities in link layer, because definitely they can be attacked, and this could be very serious as well. Okay, so another and also a bit classic type of vulnerabilities we call a blueboard. It was discovered, and it's not just one vulnerability, it's actually a family of 11 vulnerabilities. And this appeared like with a combination of design and implementation level flaw in the Bluetooth Classic protocol. So what happened? So main issue was in the secure manager protocol. And let me explain to you what is the main root cause of this vulnerability. So if you know, so when you try to pair your Bluetooth device with another, let's say, device, because Bluetooth is about pairing, so you know it shows you a prompt to accept the connection or not. So now this you can see because you have a user interface. Think about the device which don't have user interface. So in that case, the pairing still needs to happen to make this Bluetooth thing work. And this particular configuration where the pairing happens silently is called just work configuration in Bluetooth. So now imagine not the device which have to be paired using just works, like this particular configuration you see. Let's assume a device which just pretend to have the just works configuration. So let's say you have a user interface, but you just pretend to have not a user interface and want to work with the just work configuration. So in that case, what it was found that the Bluetooth protocol allows a pairing to happen silently. And once the pairing happens, you know, anybody can pair like this, exploiting this vulnerability. And that is the front door of many attacks that was conducted by Blueboard. But the main root cause was to, in fact, exploit this just work configuration, which, as you see, it in fact is meant for devices which has no input and no output. Now, if you pretend to be a device which has no input and no output, the protocol still allowed to do the pair. Okay, so now what we will do, we will take a break to continue to the next session.
We'll now be having a short break. Feel free to stretch, grab a coffee, and refresh yourselves. The tutorial will resume in about 5 minutes. Ladies and gentlemen, welcome back. The research tutorial will now resume.
Let us continue. So the next one that we want to discuss is about key negotiation of Bluetooth attack called knob. So this one also at Bluetooth protocol standard, so which allows in fact to exchange a length of key which is just equal to 1 byte. And when it is just 1 byte, you know, it is possible to just brute force the all possible values of key and in fact connect to the device. So it's just the vulnerability is that it was discovered that the standard allows during when the connection happens to exchange a key length which is just equal to 1 byte. And in fact, this is since it's a design level, most of the device which is implementing Bluetooth protocol was also affected. The most recent one is perhaps called bias attack, and this is also a design level vulnerability that allow you to impersonate a certain device. So on the left side, you see there are two persons like Bob and Charlie, but the Charlie is malicious, who is pretending to be Alice. So for example, Bob wants to make a connection to Alice, and it sends certain connection request, and well, what the Charlie does, and you know, in Bluetooth, actually you have a device has a particular address, and this address can be copied by anyone. So what Charlie does, so Charlie basically pretend to be as Alice, and then what it does, it basically asks to switch the role of a master. So for example, in Bluetooth, you have this master and slave, and previously Bob was the master and Charlie was the slave. And at this point, what Charlie wants is to switch the role as master. And why, it will become clear in a moment. And since Bob see a particular valid Alice, like just Charlie pretending to be Alice with a valid Bluetooth address, it accepts the switch of the role. And then, you know, at this point, when the role switch is accepted, Charlie becomes the new master. And after that, the authentication happens. And in this authentication, the keys are exchanged. Now, typically in this key exchange procedure, what you see is this KL. This was negotiated between Alice and Bob. But now that Charlie has become the master, it doesn't need to know the KL at all, because now that it has become the master, Bob has a valid Bluetooth address, and it sends the RS, which is some sort of key, and in a completely valid message exchange. And even though Charlie may not know the actual KL, so this can actually proceed to authentication and in fact communicate with Bob pretending to be Alice. So this is called bias because this one is trying to impersonate a certain Bluetooth device. So now what we discussed is something called Swinetooth. So this was in fact from our group, and all these vulnerabilities were implementation level, but there with some caveats, so which we will discuss in a moment. So this was disclosed in fact this year only, and they have quite a serious implication. First of all, the vulnerabilities were quite a few, and it's not just this many. It is possible that they may exist in other type of Bluetooth chips as well. So if you are wondering about the name, how this Swinetooth name comes, so it actually named after the son of King Harald Bluetooth, who was actually the person when the Bluetooth name appeared. And this Swinetooth was his son who revolted against Bluetooth. So that's how the name Swinetooth comes. So when this was tested in our lab, so we found several popular Bluetooth chips were in fact affected. And not to mention, of course, these chips are used in many popular IoT products, and they were also affected as well. It's just the nature of attack might differ depending on the IoT product it is employed, and also open source BLE stack. So there has been a second batch of these vulnerabilities, which was which actually now is publicly disclosed, but initially it was privately shared with the government agencies in Singapore, and they happened in other devices which could be also more general than the devices that we tested. And Bluetooth SIG, in fact, wants to have the early access of this exploit because this exposes some serious flaw in the link layer of the Bluetooth Low Energy. And as far as I know, even though there has been many vulnerabilities, most of these vendors have already patched all of these things, except in our knowledge, Microchip haven't. And yeah, so, but this is always the case in case of many vulnerabilities as well. So just to give you a brief overview of what are these type of vulnerabilities. So they can be classified in three categories: crash, the deadlock, and security bypass. So perhaps again, the most serious one is security bypass, which allow you to bypass certain security feature, whereas crash and deadlock, it might depend on which type of device that the chip is being employed. All these code are in fact publicly available for testing arbitrary IoT devices, because the good part is that you could in fact take the exploit code and test your IoT device, even though those IoT devices were not tested by us. The interesting fact here is that you see this we call anomalies. And anomalies mean it's not security issue, but they are violating the standard. The interesting thing is that the two security bypass that you see here, their root cause in fact is a non-compliance. And I will tell you what is exactly this non-compliance in a moment. And in the second batch, it was mostly crash and deadlock. Like one of the things is very interesting here is that one of these vulnerability appeared in the Bluetooth IP. And you know, when you have the IP, this IP is used by many system on chip, like Matthews described in the beginning. So that's why we are not aware of the total number of system on chip vendors affected for this channel map fault, because this in fact affects like at the IP level. Okay, so let me now give you some example of these vulnerabilities. So at the left side, you will see the normal Bluetooth connection procedure and pairing and encryption. And on the right side, what you will see is where these vulnerabilities actually appear. So what I will try to convince you during by showing this example, you will see that they appear for some very, very specific corner cases. So it's almost impossible to find this manually. So we do need better testing tools for testing or validating wireless protocol. So the first one, what you see here, well, let me first briefly explain the Bluetooth connection procedure. So when you pair a peripheral, Bluetooth peripheral, so they, you know, advertise to different channel, and then the master, for example, like your smartphone, they in fact initiate the connection request, and during this connection they exchange a lot of information like version, feature, length, the MTU length, etc. And then during the pairing procedure, you get the key, you negotiate the key, and this key is used in the encryption. And finally, there is a key exchange procedure which distributes the key. So roughly, you can think of like connection, pairing, and encryption. So like three high-level procedure that happen when you are pairing, when you are basically connecting the two devices using Bluetooth. Now, this particular vulnerability appears in this stage, as you see the Zoom version here. So this invalid connection request, so why we call invalid? Because here the central is acting as a malicious entity. So if you perfectly implement the protocol, of course, this will not happen. But if you connect with a malicious entity, for example, like you saw before, that it's possible during the crack vulnerability as well for Wi-Fi. So what we do, you see the payload here. So this is a normal payload, and this payload has certain field like interval and timeout. So these are used for the Bluetooth connection. For example, interval means like the interval between two messages, timeout might be the timeout for retrying. So what it should be, the value should be non-zero in millisecond when you multiply by 1.25. So they should never be zero. But if you send them zero, what happens is that, so the device completely stop advertising. And in fact, to enable advertising again, you need to manually interfere to the peripheral to initiate the device. So this is kind of a denial of service. By sending certain malformed frame with certain field cleared out, you launch a denial of service attack. So let's show you the next example. So this one also happens at the earlier stage. So you see again in the zoomed in version, so you can see these two bits, NESN and SN. So these two bits are used by the central and the peripheral when they actually send a message and acknowledge the message, to set the bit to clarify that they have sent certain packet, and to set the bit to clarify that they have acknowledged the packet. So as it turns out, if we send an anchor point with both the bits being set, this in fact creates a kind of invalid operation at the peripheral side. And this invalid operation, what happens is that it completely gets confused. And when you keep retrying sending different packets, the buffer gets full at the peripheral side. And you can in fact use this kind of vulnerability to in fact overflow the buffer. So the next one is perhaps the most simple one, and you might wonder why this was not in fact found before. But unfortunately, this is also, I believe, or we believe, due to the lack of testing. So what happens here? So as you see, different connection request messages here. And in the connection request message, you have this header, and in this header, there is a bit called, or there is a field called LLID. It's a 2-bit field, and which can have value 1, 2, or 3. The 0 is not defined, and 0 should not be there. It could be 1, 2, or 3. But if you clear the bit, what happens is that, in fact, the peripheral enters a faulty state, and it completely prevents the user to communicate with the peripheral. It's more like a deadlock, so you cannot at all communicate with the device. And again, this requires for the user to manually reset the device because they cannot communicate anymore. So you can think of, if you have a device which you are supposed to control by smartphone, and someone can launch this attack, every time you have to go to the device and need to manually restart it to operate. So which completely defeats the purpose of IoT. Okay, so now this is also a simple but not easy to find, but easy to understand. So again, in this request message, so what you see here, there is a payload which is supposed to have a particular length. And in this length, as you see, this length is 2 plus 3 plus 4 plus 5, only 5 bytes payload. But of course, given that we are a malicious central, we can send any length. So this length is supposed to capture the length of this payload. And as it turns out, this length, instead of giving 5, we can of course give something what we want. And 247, in fact, it could be any value. And now what happens is that, you know, this allows this, in fact, exploit you can exploit this vulnerability to overflow this buffer, because now you are not just copying 5 bytes, you are copying 242 bytes, which in fact leads to an overflow usually. And interesting thing is that this particular vulnerability, the same test you can use to trigger to actually attack in many devices. So this also points to the fact that this particular protocol layers are not tested properly. Okay, let me now show you, so that one is perhaps quite technical, but let me first show you now an example video, how this attack actually happened in a real IoT device. So you saw that we are actually attacking the device is restarting, but how does it look in a real IoT device? So this device that you see here, so this is an Eve smart plug, which you can control through mobile. This light you see here, this particular box, this one is a light which should be on when you switch on the plug. So now what we are doing, as you see, this one is, we are trying to attack. So right now you can see that the plug has a green light because it is on. But now when we launch the exploit, you will see that the light will turn off. So as you can see the implication, anything that is attached to this plug will also switch off as well, because this is a smart plug. And similarly, we can launch the exploit once more, and you could see that it will switch off again. So once it switches off, of course, the internal application software will restart the plug again. And that's why you see red light, and then it will restart again. Yeah, but the point is anything that was connected to the plug is already gone. Okay. So now let's continue with some more example that we have. So this one is slightly more complicated than the one that I have described, which was perhaps changing just one field without implication on the other. But here you see something called truncated L2 cap. So L2 cap is a one layer in the Bluetooth protocol. So here what you see, this particular payload has an L2 cap header, which is 4 byte. And this length that you see, LL length, has to capture the length of the header plus the length of the payload. So which means, like, you know, it has this LL length has to be at least 4. And it could be, I think, at most 17, but not important. But here, since the header is 4 byte, as it turns out that the payload size is, you know, 3 byte. So this is how it is supposed to be. So if the payload size is 3 byte and the header is 4 byte, the length should be 7 bytes, not 5 bytes. But here, well, of course, this is a malform frame. So what we could do, instead of sending 7 byte, we can send 5 byte. And what happens in the reception side of the peripheral? Now it allocates a buffer which has length 5 because it takes the length from here. But you have a payload which is of 7 byte. And now you copy 7 bytes into a buffer which is allocated only 5 bytes. So obviously you are going to overflow the buffer. So now you can see, like, by kind of tuning the length of the payload and the length of this particular field, you can actually do a lot of stuff. For example, buffer overflow, or even in the extreme case, remote code execution. This one is in fact in the same L2 cap layer. So as I told you that the L2 cap header is 4 byte, but the L2 cap header, so LL length has to be at least 4. But this is just the opposite from the previous one. So here what we do, we truncate even more. So we just give 1. So which is certainly not possible because the minimum length for this field is 1. And if you do, again, the same problem happens. The buffer, in fact, it in fact crashes, and you can, in fact, cannot do operation anymore. Okay, so now let's discuss some different cause of the vulnerability. So you have seen, for instance, when the vulnerabilities appear, when you modify certain fields of the packet. But now let's assume that it's not about the field, it's about something about timing. This is certainly, this is actually a perfect example. So the ATT request message is sent repeatedly by the central, and ideally you should wait some time before you send the ATT request again to the peripheral. So this delta T is the connection interval that was previously agreed upon. And what happens if we send this ATT request from the central too quickly? So you can think of, like, you know, you kind of like overflowing the channel. What happens is that the peripheral gets confused and the queue kind of gets full, and it could not clear this particular event. And there is a while loop, you can see, while not really even, if this bit is not set, then you could actually continue to go on this loop forever. So this, you see, we actually do not modify any particular field. What we do, we exploit the timing constraint that is natural to Bluetooth protocol. And we send too many packets in a short time, and that in fact leads to this vulnerability. Okay, this one is slightly more complicated because it requires multiple ideas to trigger this vulnerability, this key size overflow. And as I told you, this key is exchanged during the pairing process. So this key has certain length, and this key, you see here, we have given a length 253. So 253 is much more than the expected key size. So obviously this thing should fail. What happens is that, kindly ignore the below part now. So if you send this packet with an oversized key, the communication actually continue, but at a later stage fail. So far so good, because still the communication does not happen. But what you could do, you can send an oversized key, and you know this key is going to be used during encryption. So not only send the oversized key in this malformed packet, you immediately start the encryption from the center. This is to ensure that when you start the encryption, this actually allocate the size for this key. And unfortunately, when you start the encryption, even though you should not start the encryption here because the pairing hasn't finished, you actually accept this request, and the thing actually crashed because this is an oversized key. You should not have this oversized key at the first place. Now, this is different from the things that you have seen before, because to trigger this vulnerability, you need both of these ideas. So you need to start encryption much earlier than actually is expected, because the key is not actually negotiated. So you shouldn't start the encryption, and also you need to sign an oversized key. So these two ideas combined, you trigger this vulnerability. This is a relatively simple one, but still quite important. So in case you, in the pairing stage, you choose legacy pairing, because you know in Bluetooth, you have legacy pairing and secure pairing. So let's assume that you choose the legacy pairing, but being a malicious central, you still send a public key during the pairing. And this one you should not send if you have chosen a legacy pairing. As it turns out that the peripheral has some sort of function pointer or some handler when you choose secure pairing. And this handler is void or null when you do use legacy pairing. Nevertheless, when you send the key, it tries to copy the key or tries to handle this key using this void handler. And obviously, since the handler is null or void, this is going to crash. So this was in fact found out, this details was found out when we communicated with the vendor, which in specific is Texas Instruments. So let me show you another demo of how this buffer overflow can cause in some realistic devices. So here you see a Fitbit device. It's quite popular, and this one we are trying to attack using our exploit. So once the exploit is run, you can see that you cannot operate the device anymore. So it's kind of has hanged. So you need to, the device will be restarted at a certain point, and then you restart this. So now you can operate on this again. But when you try to attack the device again, you see you cannot operate the device anymore. So this is how this particular exploit looks like when you launch it to a realistic IoT device. So now what you are showing a different example. So you see this square. This square is in fact a particular luggage tracker. And this luggage tracker, we are trying to attack to make its device not respond at all. And you see when you actually launch this attack, so this will happen in a moment. So now the attack is launched. And unfortunately, this luggage tracker is supposed to show you where the tracker is located. And this one is completely hanged. You cannot operate this anymore. You cannot also restart this anymore. And what you need to do, you basically need to open up the device with a screwdriver, and then you need to restart the device by opening up the battery and put up the battery again. And you can see this is quite serious if you are using this for tracker, the tracker will still show the device is located at some place which it is actually not. All right, so that was about this one. So now let me discuss some of the more serious issues which are related to security bypass. So this is very similar to the key size overflow that you have seen, because it appears at the by starting the encryption process early during the pairing. So what you see here, the encryption, as I told you, you should start after the pairing has happened and you have kind of exchanged the key. So what we do here, we actually start the encryption early, even before the key has been exchanged. Interestingly, the device actually responds, and more interestingly, the device actually starts the encryption with a 0 key. So remember, we also had this example in Wi-Fi. In Bluetooth also, we have the same thing where the 0 key is installed. And when it is a 0 key, it allows complete hijacking of the device. And more interestingly, once you have this with a 0 key, the whole key exchange procedure and the whole legacy pairing procedure is completely bypassed. So the peripheral assumes that the 0 key is the one that has been exchanged, and it actually proceed to the further stage with communication. So now you need to see the root cause of this particular vulnerability. You see the root cause is again the same, where encryption is actually happening during the pairing process. Ideally, it should not happen. So previously, we saw another example where we started the encryption process early to trigger a buffer overflow. Well, this Diffie-Hellman check, so this is some also a security bypass, but this is a partial security bypass. So as you see, this LTK that we talked about in the previous slide is computed here. But there is an additional check, which is called Diffie-Hellman check, to ensure that this LTK is the same between the master and the peripheral. Unfortunately, again, with the same reason, if you start the encryption early before this DH check, and we can do this because of the malicious central, it is possible that this DH check is completely bypassed. Nonetheless, this is not as serious as the previous one, where it installs a 0 LTK. It still installs an LTK. So thus this LTK needs to be known by the malicious entity, like he has probably completely compromised the device. But otherwise, this cannot be fully exploited. Nevertheless, it weakens the security of the protocol implementation. So finally, this is a very complex one, and you might wonder how someone can even find this one. So this was in fact appeared due to some very specific issues in a device called ESP32, but it can still appear in other devices as well. So let me start with the normal behavior. So what happens, if you try to exchange a very large packet, so I think the most important part is here. So if you try to exchange a very large packet, so what the Bluetooth controller does, it fragments the packet. So as you see here, so basically a large packet length was negotiated, and it basically fragments the packet into two. And then when it in fact fragments the packet, after it finishes communicating the two fragments, it in fact set the field as the number of completed packets to be 1, because the 2 fragment equals to 1 completed packet. And then you see this check where it checks outgoing packets, whether it is greater than or equal to number of packets. So this is outgoing packet always has to be more or equal, because this is the packets in the queue and number of packets is the packet that has already been delivered. So this check has to be satisfied. And if it is satisfied, then you go proceed normally. What happens, the only difference that we make, instead of normally communicating, at this point, we send a malicious packet with a wrong message integrity check. And this particular malicious packet triggers a MIC failure at the peripherals, the controller side. And when this failure happens, the problem that occurs is that somehow due to this failure, the number of completed packet doesn't return the number of completed packets. So it actually returns the number of fragments, because the packet was high. You see there are 2 fragments. In fact, due to this failure, it returns the number of fragments instead of number of completed packets. Still good, still okay, although it's a non-compliant, it's still not a security issue. But now what happens, this particular check fails because the outgoing packet is 1 and number of packet is 2 due to this failure. And this check failed, and then what the controller tries to do, it actually tries to restart the device. Unfortunately, it is not able to restart the advertisement anymore. And this is where the vulnerability actually appears, where the denial of service occurs. So the root cause was this particular message, and what it triggered is to return a wrong number of completed packets by the Bluetooth controller. And then even if you try to fix it by restarting the device, it doesn't occur because it still does not advertise anymore. All right, so now I think I have given you some ideas on how these vulnerabilities, in fact, or some example of these vulnerabilities. So there are many things to summarize from here. So some of them appear at the design level, some of them at the implementation level, some of them due to the confusion on the standard, because the Bluetooth standard never clearly mentioned what happens when you start the encryption during the pairing process. And different vendors implement it differently. And as you saw, when we were starting the encryption process early, it in fact led to different vulnerabilities. So we'll come to that a bit more at the end. But now, I guess I have convinced you that most of these vulnerabilities are quite tricky to find. There is no way you can find them manually. So we need tools and technologies to find these vulnerabilities. And that's what we are going to discuss now. Unfortunately, as we already discussed at the beginning of the presentation, there is a very much lack of automated tool to find vulnerabilities Wi-Fi implementation, and also for Bluetooth as well. And the main reason is that you need a lot of control on the packets. For example, for Bluetooth, you need to control the link layer packets directly from the user space. There is no tool before certain research happened that could actually do that. And this requires a very heavy research as well as engineering effort. And that's why the testing has been very limited due to these challenges, due to this isolation between the user space and the link layer. Nevertheless, there has been some tools, but unfortunately, most of these tools are very specific to some attack, or you need to manually write certain test cases to trigger vulnerabilities. We don't want that. We want this to be kind of automatic. Fortunately, fuzzing we are mostly aware of. It's a technique to find issues in software, especially security issues like crashes mostly. And it has been very successful, at least for pure application software. But there has been, of course, limited effort in wireless due to the challenges that I mentioned. So this is kind of architecture that we want to envision for testing not just the current wireless protocol, also next generation protocol. So you see this has basically 5 different components. One is the protocol model, which is kind of capturing the behavior of the wireless protocol. Then we have packet manipulation. So you see that we were actually manipulating packets. So how do we manipulate? So this is automated by packet manipulation. You are seeing that we were sending packets at an inappropriate time. For example, starting the encryption early. So this has been done by packet redundancy. Packet validation is to check automatically the response from the device, whether it has been crashed or whether it is sending a packet which it is not supposed to. And finally, we have but not the least, in fact, very important one, we have the optimization module. And this optimization, in fact, dictates or directs the fuzzing architecture or which parts of the field of a packet you should modify or which packet you should send out of order, like redundant packet, so that you have more probability to find the vulnerabilities. So now I will hand over to Matthews so that he can describe in a little bit more detail about the challenges in each of these modules.
So as Sudipta mentioned, we have several components, each one responsible for one part of the fuzzer. And note that the one component that is extremely important is what we call the packet redundancy. So as shown before, many of the vulnerabilities, they rely on two behaviors. So one of them is mutation, and the other one is the sending packets out of order. So the packet redundancy is here to ensure that and ensure that we can find this complex and out of places vulnerabilities. So, but before, of course, the work that mostly got the attention of the community was Swentooth, the work of Bluetooth Low Energy. But we first start with Wi-Fi, right? So I'm gonna show you the steps of how we designed Wi-Fi, the model that designed for Wi-Fi, to be able to first and start the work there, and show how we handle each one of that components there. So for Wi-Fi, I think most of the people are aware of the normal architecture of the Wi-Fi, which will have the access point, other devices there. So then, similar to other devices, it can be peer-to-peer devices or sort of gateway. But we start by focusing only on the access point, and then try to fuzz the client in a sense. But first we always need to look at what is the lowest possible information passed between two devices, right? And this is the MAC frame for Wi-Fi. Here it shows like some of the fields here. And these fields, each one of these fields does a specific thing, but particularly there is always a type field which identifies what is the type of the packet and what is its purpose. So here for Wi-Fi, we have these control frames, management frames, and data frames. Control frames are to manage the network itself, connect to enable the client to connect to the access point, also manage addressing, acknowledgement, and so on. The data frame is the one that actually sends data packets, so HTTP packets, although they are mostly encrypted once the client connects to the access point. The management also handles the functions of our network, particularly for the connectivity, authentication, and there is other packets related to the encryption and the key exchange also. So now there's also a certain mapping that it's out of independent of the wireless technology. There is also this mapping between the types of the messages and the OSI layers, so the layers of the networks involved. And although the physical layer we are always trying to not touch, it's always difficult to mutate packets that are just on top of it, such as the MAC layer, because they rely on certain timing features. So for example, acknowledgements are ones that happens, as shown previously, one of the examples, the acknowledgements for Wi-Fi happens too fast. So for example, generally the acknowledgement between two messages happens in 10 microseconds. So it's something that if I try to manipulate and process these messages in real time is not that much guaranteed by the operational system. And sometimes you need to do some changes on the Wi-Fi hardware, for example. So to solve this issue particularly for Wi-Fi, we had two issues. So one issue was the high latency. So because we want to model access point state machine, we want to make it as flexible as possible. And the first thing that we saw to make it possible is to use the Python, because there is some popular libraries which we could boot our model upon. However, Python as a language known to be slower because it's runtime based. And however, we still need to find, is it possible to keep the flexibility of the model and still make the model work properly, even with these timing constraints? So then we actually need to give a look on how the Wi-Fi hardware itself is handled. And we start by using a Wi-Fi dongle. So here, as an example, this is Ralink USB dongle. And this is it's connected via USB. So there is a driver that handles the communication between the operational system and then the Wi-Fi radio itself. So the normal communication or data path that goes from the operational system to the Wi-Fi radio and then to our device is during the kernel space. There is this multiple interfaces and components. And for example, if we're trying to run a further software here on this user space, there is no escape. We need to go out with all these components, and this increases latency, which means we can lose the response from packets. So if we delay too much to answer the client on the model, we lose this packet, and then we cannot proceed the state machine correctly. We need to then retry a lot. So to solve this issue, the first thing that we done is, okay, let's try to redesign a bit, simplify a bit the communication path. So instead of going all the way the normal ways of the operational system, we simply use a direct communication via inside the driver to communicate with the Wi-Fi radio in which uses USB. So instead of relying on all those components, we simply communicate directly to the Wi-Fi radio. And the advantage is that we can now easily configure the hardware registers in the Wi-Fi radio. And this is particularly important because we can control the Wi-Fi radio to operate in the mode that we want. So because we want to fuzz, we need to change the mode of the Wi-Fi radio to monitor mode, which is a common mode for Wi-Fi for you to sniff packets and also to send packets. However, the acknowledgements are not handled, and we still get this retransmission error. By configuring the radio register, and gladly this USB dump is one that is known to have a data sheet with all the hardware register documented, it's possible to modify certain hardware register to automatically answer these acknowledgements. So given that, this low latency acknowledgements that is really crucial. Once they are solved, then the model works are as expected. The only timeout that we need to worry about is the normal host side timeout, which is in the range of then 10 milliseconds or more. So it's no issue at all for our operational system to handle this timing. Then of course, once the interface issue is solved, the wireless interface can manipulate the packets without this time constraints. We can now focus on the model. And this is particularly the model for Wi-Fi, the one that we tested to test different messages. Each one of these states corresponds to a certain message. So we have here, for Wi-Fi it's known, we have the network discover, so we have the model has to generate these beacon frames. Next, we have the model for the encryption process, and this is important because for many wireless technologies, there will be certain security features for authentication. So it's always the case that you may need to include this in your model, this security handling. Just as a comparison, by default, the Wi-Fi radio mostly already handles the encryption because it has more capability and so on. So these encryption features can be mostly offloaded by the hardware itself, but here on the model, we bring it completely via software. And of course, after that, then we have the normal connectivity, which is mostly encrypted for either personal wireless networks or enterprise networks. By enterprise networks, I mean the ones that you have to type not only the password, but also your username, which it adds this EAP state there. Normally, for a normal Wi-Fi password, which is called the Wi-Fi WPA2 personal, we only have the normal states here, but then we go to the handshake directly. So the EAP is one state add only for enterprise. And now then we ask, okay, but where is the issue, right? Because we want to fuzz this, and the main thing that we are aware is that, okay, there is many types of packets, right? So how can we decide which packets in which states to mutate or duplicate in order to trigger some certain odd behaviors on the device? So then here I starting by showing how the fuzzing works. So we have the definition for each types of packets, and here I show an EAP packet as an example, and a certain packet. It's known like in networking, each packet has a different protocol inside. So one packet has multiple protocols inside it, and each different protocol we call it layers, and we assign different probabilities for each layer. So the idea is that to use these probabilities, given a certain chance that this probability is high, is chosen by the fuzzer to be mutated, it will mutate only certain specific fields. So we can, if later I'm gonna exemplify, but if later we change these probabilities differently for each layer, it will direct the fuzzer to specific layers or fields. So of course this is layers, but if you go inside each layer, we have different fields. So for the fields, we also assign a certain probability value for all fields with the same layer. to ensure that we are also mutating each field independently based on the depending on the value of this probability. It's important to mention that we assign the same probability for all fields with the same layer, because it reduces the number of parameters to be optimized. But also, even then, even if you are using the same probabilities for the same field of a layer, it is still possible to mutate this individually. Just by chance, the fuzzer will automatically mutate this differently. And another example, then the other layer, you can see that different probabilities assigned. But the fuzzer needs to receive this as an array. So here it shows how a certain packet generates the set of probabilities. So we can use this to optimize. So for each state machine, for each state of the state machine, you have this set of probabilities, and it's a flattened array of probabilities that later we try to optimize to certain directed fuzzer the specific fields of the state machine. Then we have also important thing of all this, because now with all those vulnerabilities going on, how can we detect vulnerabilities other than crash? Because for fuzzer, it's normal to detect crashes when the device stops working. But what if there is certain anomaly? And by anomaly, I mean a certain bad response, a non-compliant response. So it's good that we also try to validate the response. And the logic that we do this is by, in each state, implementing certain rules, the expected layers or rather expected types of packets for each state. So here, as an example, we have here the first we start by the validated packet. So let's say that we are on the state association, and the expected layers or types are configured there, and these are based on the standard. And if you receive a packet which is expected, it's okay. It's a valid message. But if you receive a packet that is not expected at all, then there is some issue. In this case, if you are in association, it means that authentication was already completed. So if you receive it again, some issue may be presenting on the device there. So then on the optimization, given that we have this both the access point, which is the fuzzer itself, and the client, the idea is that we use a protocol model, and then we define where the iteration will start, because if you need to optimize, you need to define where the new iteration will start. So because we are the access point, each time the client connects to us, it will start a new iteration. And for each state, we have these mutation probabilities as a flattening arrays, and we assign post functions. But because we are doing this over the air, and the idea of this fuzzer, because we need to be as flexible as possible to test different devices, it's good that we think in a way to make it easy to get metrics even over the air. So one of the post functions that can be used, and in one of the papers that we named Greyhound, we tested this for post functions. So we used the anomaly count, which is the total number of anomalies, which can be also vulnerabilities found during the fuzzing process. The anomaly period, which tries to reduce the time between finding two anomalies. So so then the rationale is to try to find anomalies consistently and faster, so it's easy to analyze, for example. Iteration time, which tries to make the fuzzer directly the process to make the client connect faster, and maybe get the client to trigger some vulnerability associated with too many packets being processed or time-related problems. And then transitions, which is to maximize, and by maximize the transitions, we try to make the optimization process try to focus on vulnerabilities later on the end of the state machine. So it incentivizes finding issues on later states here, such as the EAP for handshake connected. So the state machine does not get too much centric on the early states here. And the optimization, particularly the optimization that we start using is this particles farm, because it behaves in our experiments and also compared with other research, it behaves well with some random behaviors during the optimization process. So even if the the connection between two devices are identical. Because of the environment, there will be some packets lost. Maybe you need to reconnect again, and certain host functions may be different, even though the iteration is the same. So it's important to get optimization which does not vary too much in face of maybe random variations of your environment or setup. So here it showed the setup that we did for Wi-Fi, and here we have the computer running fuzzer software, then the fake as the fake access point, and over the air then we test the fuzzing target. So this is the relevant targets that we show here. So these two IoT devices, Espressif 8266 and ESP32, the one that we found in the vulnerabilities. We also test with a car Wi-Fi media center that we were able to, because of the validation and the approach that we use to employ the components, such as the mutation duplication. We can also trigger, we were able to trigger known vulnerabilities such as crack, particularly for this Alpha Media Center. As it turns out, it was auto updated, and its software, it was around 2016, and crack was mostly disclosed and patched around 2017, 18. So clearly, it wasn't patched, and we could also find this by systematically running the fuzzer. And now going to the Bluetooth energy, what would be the difference? The difference when changing technologies, right? As I'm gonna show, the difference was actually greater, and much more work actually needed to be done to enable you to send packets freely over the air. So here I show the stack with the Bluetooth. You can search like a Bluetooth Smart, but or you can also they can also identify by single mode of Bluetooth low energy. So this was introduced since Bluetooth version 4. And we have here a scenario, like we have the smartphone as the central, and then the smartwatch, the peripheral, which is mostly your IoT device. And the funny thing about Bluetooth energy is that it behaves, you can think of in contrary to Wi-Fi. So of Wi-Fi, the access point is advertising. Here is the other way. The peripheral, the device that you are trying to connect and communicate, advertises to you. So it's like it seems like the other way. And here it shows, if you're going to start the modeling, how the Bluetooth energy stack works, it's important to know that we have the separations here for Bluetooth energy. So we have the controller, which handles the link layer, which is similar to the MAC layer with the Wi-Fi. Then we have the host layer, which is the layer is used for the product itself to behave, to do a certain thing. And mostly this host layer is, on the standard, is isolated. So it's supposed to be isolated, running on a different hardware, for example, or if it's running on the same hardware, the software must present some sort of isolation. Of course, this will introduce complexity on implementation. So now another example, Bluetooth particularly is getting much more complex. So there's also this new mesh, Bluetooth mesh. It introduces the more protocols to the host, but in parallel it behaves some sort of a on top of the existing technology. So you can think that more and more versions of the standards of a particular technology, there will be more overhead on the number of layers introduced, and more vulnerabilities can be found because of the complexities to maintain all of this. And here it shows how is the frame of the Bluetooth energy. Because for Wi-Fi, we had this other showing all the types and so on. For in summary, for Bluetooth Low Energy, we have this this payload here, and it's important to mention that these preamble accessories until the payload, they're all closed on the controller. So this is supposed not to be manipulated by the host at all. The only field that you can manipulate on the Bluetooth energy is until the speedy payload. So only the host layer you are free to manipulate. But if you try to look inside the link layer, it's not possible to, by default, to manipulate these fields because of this isolation imposed by the standard. So the way that we do to avoid this limitation of the isolation of Bluetooth energy, we think of introducing and implementing from scratch a Bluetooth controller. But the idea of this controller from scratch is to be non-compliant by default. And another concept that we try to introduce, just to make it work with fuzzing, is to move the link layer completely to the host. So because we are trying to do a model for Bluetooth Low Energy so we can fuzz, it's good that we can model the link layer on the host itself. So if you can move the link layer, albeit this is some sort of a taboo on the standard, because the link layer must be handled in a hard time device, and it has timing requirements. So what we do to make this work and move the link layer to the host so we can fuzz is to implement the controller from scratch, such as it handles the basic timing features of Bluetooth Low Energy, such as the acknowledgements and transmissions, and any different packet which is not acknowledgements, but it's the link there by itself. Then we just forward to the host. And by doing this design oriented on the host side, we're able to open up the link layer, and now it's much more easy to test and research the link layer functionality. In comparison to other works, normally vendors use much more expensive equipments to test the link layer implementation. Usually devices that they are also used for certification cost for around $5,000. But with this sort of design, we can use a device which goes around $5 to test the link layer much more easier. It's important to mention that in one case, one vendor had difficulties to replicate one of the anomalies, but because we did this controller from scratch and it's made to do fuzzing, it was much more easier to do, whereas they took some time to replicate using their expensive equipments. And going back now, how these all come together, showing how the fuzzer handles this by, for example, showing a vulnerability that needs to handle both mutation and duplication. So here on the top side, we show the state machine. Here we are on the pairing request state, and we receive a response from the device. So let's say that the peripheral is on the left side here as the microcontroller, and let's say that on this state we send a pairing request with a mutated field, and the name of this field is key size. On this particular instance, the device responds to us, and the interesting thing is that we are not expecting to receive a response after we fuzz. We introduced this idea of rejection layers, which is the layers that we're expecting to receive after mutation. And because we mutate the essential field, the device is not supposed to respond. It's supposed to respond with a failure message. And this is okay, an anomaly for now, but because on the same iteration, the fuzzer also sends repeated packets, it's possible to trigger the key size overflow, which Sudipta mentioned. So if this is a combination of mutation and duplication, and in this instance, if another packet sent, in this case LLA encryption request is sent to the device, then it's where the device tries to use the information from previous field and then crashes. So yeah, he on the bottom side shows the Russia capture and how the device misbehaves. And here I'm gonna show just a brief demo of how the state machine navigates through a Bluetooth tag. So I have here a common Bluetooth tag. Not sure if it's clear to see here, but just a common tag here, a Bluetooth tracker, which people usually use to track their belongings. And to the left side here, I have my smartphone, which will run the fuzzer, and it's attached to the dongle there. So this fuzzer dongle, which I just discussed, is attached there, so we can start the fuzzer and then connect to the target device, which is the peripheral that we want to fuzz. So just to show here, we can the first thing to make this Bluetooth fuzzer work, we need to know the address of the device. So the only information that we need to know is the address of the device. In this case, is this tracker here, which has this address. But in this case, it's already configured. So I'm going to start the fuzzer here to show. Give a moment, it's loading. Yeah, so now I switch to the user interface. So the screen is a bit tiny here because it's running on the smartphone. but this is to show the navigation. So this is our model, and this dense part here is the link layer, and the other parts here are the high level protocols on multiple energy, which is like the L2CAP, ATT protocol, and so on. And particularly for this device, it does not perform pairing. So here it shows like the device does not, the model is not proceeded to the other states, as this device does not support the full range of Bluetooth low energy features. And so the only thing that we need to configure is the slave address. And of course, the fuzzer is enabled. So sometimes the device times out here, and then we go back to the first state, which tries to reconnect again. And the bottom side, it shows the state here. Here, pairing request, and it tries to perform the pairing, but the device does not respond. Goes back to scanning, and go back. So this demo show you what was the generic idea. And here the device time out a lot, so it shows like a crash. Although sometimes the device misbehaves and then times out a lot. So here it shows an example of how we are modeling for both Bluetooth Low Energy and Wi-Fi, how we are handling the fuzzing process. So we always try to model and then handle the states separately, and try to make the fuzzing naturally trigger certain situations which can trick the device on vulnerability problems which the vendors that are doing the implementation didn't think of. And this is combination of mutation and duplication. So now I hand over to Sudipta.
I will just quickly conclude the presentation. So what we have seen that many of these vulnerabilities appear even though they are certified, the devices were certified. So all these devices we tested had the latest SDK, but they still appear. And in fact, there has been a lot of issues in the protocol standard. They conflict with each other. And that in fact lead to certain vulnerabilities. And in fact, the producing patches is quite complicated because of the way the IoT supply chain works. A certain device, like medical device, can take several months to receive patches. And finally, some of the implementation might be in the ROM, which was in our experience that requires a very long time to fix. So we actually believe that the type of vulnerabilities we discuss is only a start, and we already see many such vulnerabilities are coming. So I think the way we should think of IoT design to have less reliance on the communication module, and whether we can design IoT in that way. So just to conclude, as I show you that the standard itself, Bluetooth does not clarify what happens when you start encryption during pairing. And this was the main issue, which is not even clear in the standard. So even though these are implementation level vulnerabilities, they appear due to this, the ambiguity in the standard. So both the security bypass, which are the most critical one, appear due to the ambiguity in the standard, which also need to be clarified better. So that's about it. And I conclude the presentation here, and the references can be taken from this slide. Thank you very much.
We will now proceed with the Q&A session with Professor Chattopadhyay and Mr. Garbellini, hosted by Dr. V.V. Suhendra, Executive Director of the Singapore Cybersecurity Consortium.
Thank you, Sudipta and Matthias, for delivering the comprehensive tutorial, and good afternoon to everyone joining us virtually. So let's get to the first question. Matthias and Sudipta, please do unmute so that we can talk to you. Okay, so the first question here is, what are your thoughts on new security implications of 5G on IoT systems? Now that, yeah.
Thank you, Vivi, for the introduction. So, in my opinion, of course, 5G has a lot of advantages in terms of applying to IoT, in terms of latencies and stuff. But what we observed in our experience is that the protocol, as it goes more and more complex, the chances of having vulnerabilities are also more. So Bluetooth was one of the examples where it was a lot of layers where there resided a lot of vulnerabilities. So given that 5G is more complex protocol than Bluetooth and stuff with a lot more layers to explore, I expect that there would be quite a lot of space for security research in that domain. So security issues in 5G for IoT is still quite open. There has been work that shows some issues with some manual and extensive effort, but it requires some systematic investigation.
Okay, thank you for that. Matthias, anything to add?
Yeah, so I believe the paper's definition was called 5G Reasoner. So gladly, there has been some previous work on 5G design itself. But it was good to indicate that there are people concerning some security issues in 5G. And now, because it's the quantity of IoT devices now would expand using this new technology will be immense. So the requirement to defend against like botnets is also another concern for 5G. But gladly, 5G is now adding more encryption to the one of the user planes, which were previously not used in 4G. So in terms of security, they are adding more features in this regard.
Okay, let's move to the next one. So this question is asking whether there are AI-based approaches to discovering vulnerabilities in IoT protocols, since I think you shared in the talk that it's actually quite a lot of challenges to discovering this. So can AI help, since we discussed AI yesterday? Yeah.
So not in my knowledge that there is any AI-based tool that discover protocol vulnerabilities, but that said, some of the tools are commercial, like some of the example that we show, and sometimes it might be a bit difficult to understand the underlying techniques that they employ inside. But AI-based tool, again, the main issues that they face is I think, to find out these unknown and zero-day vulnerabilities. And given the nature of such complex protocols, I doubt whether there exists any as of now. Matthias, you want to add anything here?
I think you summarized well.
Okay. Moving on. So, okay. Notice that BLE, Bluetooth Low Energy, appear a lot in your vulnerabilities discovery. Do you think they are due to compromises in the protocol design to accommodate the low energy mode?
Yeah, please.
Matthias?
Yeah, so this was actually something interesting that when started working with Bluetooth Low Energy, there is a lot of work in low energy. However, the protocol itself has also support to work to be more performant. So not necessarily is due to the operating low energy. Many of the issues were actually due to testing, because Bluetooth Low Energy is immensely more simple than Bluetooth Classic, the previous technology. So in a sense, I believe that there is no a certain excuse or trade-off of security when using low energy. The only one of the points is that the devices running the protocol are less capable, but still some of the issues were really fundamental. So it's most likely due to lack of testing.
So one point might be I add this lack of testing is more due to the link layer. So it was kind of assumed that previously that the link layer is untouchable from the user space. So what is the main reason that we discovered these vulnerabilities is not because they are downsiding features for low energy. It's more that we expose the link layer to the user space. So now it is possible for anyone to send arbitrary link layer packets, and that exposes many vulnerabilities which are not caught by the certification.
I see. Okay. Next question is, sorry, let me scroll. How practical are these attacks such that they will affect devices in the wild? For example, Wi-Fi attacks requiring channel amend in the middle or short-range nature of BLE. So, yeah.
I think the only assumption is that you need to be in the radio range. So Matthias can give perhaps more example on the practicality.
Yeah, so you can say that before to up these attacks, like it would require expensive equipments. But right now, you can use, for example, a smartphone. So even if the Bluetooth Low Energy is short range, it's possible to perform these attacks stealthy. I'd say that the impact of Bluetooth Low Energy peripherals, which are limited in terms of what they do, is still not that critical. But considering that Bluetooth Low Energy is a lot of devices uses both Bluetooth Low Energy and Wi-Fi, there could be some concerns regarding whether they could affect other part of the chip or not. So in summary, it's not an issue anymore to trigger these attacks. However, how effective, that would depend on the type of the product.
Okay. Next question. Okay, since Bluetooth has so many vulnerabilities, is there a commercial alternative? Or yeah, I think we will be back to the same issue. Yeah,
because this was the kind of things that we envision, that if these things are not fixed appropriately, perhaps people will go for other protocols and stuff. But of course, Bluetooth it's not that bad really. I mean, Bluetooth is one of the most important protocol to unify these heterogeneous devices. So despite all this drawback, it has many other features. I think, I mean, maybe it's too bit drastic to think for alternative now. Perhaps what we could do more is to focus on design, like secure design. Like we have had some talks before today, like which call about zero trust. And in fact, this is followed by some safety critical devices, and perhaps to put more effort on testing, which we strongly think that this is lacking in for IoT devices at this protocol level.
Matthews, anything to add?
And that, and of course, the regarding alternatives, usually for commercial electronics like smartphones and so on, there's not many options right now. But anyone working on the IoT field that are doing different products, usually there's like other popular protocols such as Z-Wave, LoRaWAN, ZigBee. So there is still alternatives, although more for special devices, not for usually consumer electronics.
Okay, let me see. This one is related. Okay, a new question coming. From a Blue Team perspective, is there a way to probe wirelessly whether existing devices are susceptible to such vulnerabilities?
Yeah, that one is a bit tricky, because some of the devices affected you can get some traces, like by reading advertisements from the peripheral, checking, for example, its version, and then assuming that these may be affected. But a lot of these attacks relies on what the device will do. Then you discover if it affects or not. So it's difficult to probe, because it's not analog signal. It's not an analog signal behavior, but rather the response of the peripheral. So you have to at least connect to the peripheral, try something there to see if it's vulnerable or not. Other than that, you would need to read the version and also the vendor ID of the peripheral to guess that it could be vulnerable, but you still are never sure about this.
Sudipta, anything else to add on that?
No, I think it pretty much summarizes. I agree.
Okay. This question is a little bit related, because just now you already talked about the different protocols that with their own and all the alternatives to Bluetooth, and we still need testing. But I think this one is asking for smart homes, whether if we just narrow down to this specific application, do you have any views on which one is a better bet than others? Or it's a matter of testing.
Well, I mean, if it's protocol level, I'm not sure whether we can really ignore Bluetooth even at the smart home level. I mean, smart home, yeah. So, Matthews, anything?
So, I mean, for smart home, there is alternatives. Believe it or not, Wi-Fi is still Wi-Fi had its downsides, but is still still good for for using smart homes, mostly because the many vendors implemented the security on their user application. So there is the Wi-Fi security, but most of these smart homes have their other types of security. There's other protocols like Z-Wave, ZigBee, but Z-Wave, there is plenty of smart homes, and it seems like there is not much vulnerabilities on these other technologies. But yeah, so Wi-Fi is still on the table, so not that bad in this regard.
Okay, thanks. New question coming in. So about certification. If certification does not prevent some of the critical vulnerabilities, what other steps do we need to take? I think this refers to your you were saying that even if these protocols have been certified, but you still find vulnerabilities. So what else can we do about it?
Yeah, so this is a really good question. So there is 3 ways we can look there. So if you are a user, the only thing that you can do is to make sure that the company that you're buying the product has a good reputation, being fast to operate their products. Because at the end of the day, it's difficult to secure any technological vulnerabilities, and eventually you get to one. So at least the product vendor needs to be fast in respond to it. Not only that, but it's preferable if the vendor has some other types of vulnerabilities on top of the existing wireless technology. It also helps if the technology itself has some flaw. And the other perspective, let's say that you are a product vendor, then you are relying on the semiconductor vendor. But another thing is that the semiconductor vendor, in this case, the solution that you are trying to select needs to be really open and also easier for you to implement in your product. So in this case, you need to be careful on your software supply chain. And there's not much that you can do by yourself because the wireless implementation of many technologies are actually closed source. So only if you have a fully open source system would be like faster to patch these vulnerabilities, but it's not the case right now.
Which we also believe that the certification should be amended, and in fact, what we found that the number of tests that is done for link layer in the certification, Bluetooth certification, is very minimal. So ideally, we expect that also the Bluetooth SIG amend its certification test. So we should improve the security for IoT better, which are using Bluetooth.
Yeah, thank you for the answers. I think just nice we have addressed most of these questions here, and we are also needing to wrap up for the time that we have. So thank you once again, Sudipta and Matthias, for the tutorial, and thank you to all our virtual audience for joining the discussion. So I have you have benefited from this and also the past 2 days of the workshop. And I would like to say that Sudipta, Matthias, and the speakers who have been with us, they are all part of the cybersecurity R&D community here in Singapore. So do check us out, at their websites that you have seen during the talk, and also at the Cybersecurity Consortium for ways to stay engaged beyond this workshop. We hope to see you again. Have a good weekend.
Yeah. Thank you, Vivi, and CSICW.
Ladies and gentlemen, we have come to the end of the Cybersecurity R&D workshop. A big thank you to all our speakers for the insightful talks and to all of you for joining us today. We hope you have found the discussions useful, and we look forward to your participation in future editions of this workshop. Thank you.